is good.
Could you help me? I want to split this, right?
You want to standard or to mirror? You want the same thing? Okay.
I want to.
Quantum perplexity model checking.
Okay, thank you for the introduction. Hi, I'm Seungmin Jeon from KAIST. Today I will introduce our work on novel quantum approach for analyzing probabilistic systems. Let's start by understanding probabilistic systems. Probabilistic systems are designed to handle real-world uncertainty using probabilistic behavior. For instance, distributed systems, autonomous driving, and weather forecasting include probabilistic behavior to handle uncertainty in our reality. These probabilistic systems must be carefully analyzed before use because errors can cause significant damage in our daily life. To prevent such errors, probabilistic model checking is a great tool for analyzing probabilistic systems. It typically involves 3 steps. First, describing the probabilistic model, including states and transitions, like 50% probability of staying sunny or transitioning to rainy. Second, specifying the property to analyze, such as what is the probability of reaching a sunny state after 2 days. Then the model checker computes the result by extracting the transition matrix, performing matrix multiplication, and calculating the probability of reaching target state. This tool is robust and user-friendly as it automatically explores all possible states and performs the calculations. However, verifying large systems with high accuracy is challenging. Large systems are typically described by defining multiple variables. As the number of variables grows, the number of states increases exponentially. For n variables, each with 2 states, the total states become 2 to n. Therefore, numerical approaches require large computations because of the state explosion problem. The state explosion problem can be avoided by a statistical approach, but it requires significantly more samples than the desired accuracy. For example, to achieve 10 times higher accuracy, we need 100 times more samples. This is known as the runtime explosion problem. So there is a trade-off between scalability and accuracy. Numerical approaches provide higher accuracy but do not scale well because of the state explosion. Statistical approaches are scalable but hard to achieve higher accuracy because of the runtime explosion. To bridge this gap, you can leverage a quantum computer. But how quantum computer can achieve both criteria at the same time? Our key insight is that the computations required for the model checking can be performed more efficiently on a quantum computer. For scalability, we address the state explosion problem using quantum superposition, which is a key feature of quantum computer. For accuracy, we address the runtime explosion problem using quantum amplitude estimation, which is an efficient quantum algorithm to get useful information from a quantum state. By combining these techniques, you can analyze large probabilistic systems with higher accuracy much faster than classical computers. Let's start by understanding how quantum computer resolve the state explosion problem. In quantum computer, a qubit is a unit of information like a classical bit, but it can exist in a superposition of 0 and 1, which is a key difference from classical bit. This superposition allows a qubit to be interpreted as a probability distribution over 2 states. For instance, a 2-state probability distribution on the left can be represented by 1 qubit with a 30% probability of being sunny state and 70% probability of being rainy state. Similarly, n qubits represent a 2 to n state probability distribution. For example, An A-state probability distribution can be represented in 3 qubits, where each state has its own probability, such as 50% for sunny state, and so on. This superposition allows us to address the state explosion by representing large probability distribution and its transitions with exponentially fewer resources. Because n qubits represent 2 to n state, modifying n qubit is equivalent to modifying 2 to n state probability distribution. For example, modifying 3 qubits is the same as modifying 8 state probability distribution. This allows large matrix computations to be represented with exponentially fewer resources. For instance, a matrix multiplication of size 2n can be represented with only O(n) qubit systems. Next, the runtime explosion problem is resolved by the quantum amplitude estimation algorithm. For example, consider a property that asks for the probability of being sunny state after 2 days. By encoding weather state and their transitions as qubit and quantum operations, respectively, you can replicate the probability distribution after 2 days. But even if you have this quantum state, you cannot directly access the information. It's actually hidden, so you need a special method to extract classical information from a quantum state. QAE is an advanced quantum algorithm that provides the probability information of interest. It estimates the probability by using multiple quantum samples, where each sample represents a construction of the probability distribution as shown on the left. This process allows us to estimate the probability of a sunny state, which is close to 75%. By using QAE, we can address the runtime explosion problem, as it requires a linear increase in the number of samples with accuracy. To leverage these techniques, we need to implement a quantum operation as a quantum circuit, which is the actual model for quantum computation. The key component is the state transition circuit, as shown on the right. In this circuit model, qubits are represented as wires, and quantum gates are represented as load on these wires. The horizontal axis represents the flow of time. Here, the first and second lays are encoded in the upper and lower qubits, respectively. The quantum gate applied to these 2 qubits replicate the state transition by taking the first state qubit as input and the second state qubit as output. Formally, this gate produces the next state for given the current state. Our quantum approach works by repeatedly using the state transition circuit. The overall workflow is as follows. First, given the model, we construct the transition circuit by translating model into quantum circuit. Next, given the property, we construct the model checking circuit by translating property into quantum circuit. For example, if the property asks for the probability of being sunny state after 2 days, we first encode the initial state and repeat the transition circuit twice. Then we encode the result, probability that sunny on day 2 is true, into the bottom result qubit. The final step is to extract the probability that the result qubit is in the true state. This is achieved using the QA algorithm, as mentioned earlier. The main challenge in this workflow is translating the model into a state transition circuit. The other steps are relatively trivial, involving the repetition of the transition circuit and the use of the well-known QA algorithm. So I will show that how to translate the model into a quantum circuit. Here is an overview of how we translate the model. To build a transition circuit, we translate the model in 3 parts. For example, the weather model on the left is divided into 3 functions: guard, choice, and update. These functions are translated into corresponding circuits as shown on the right. The guard circuit for evaluating the guard condition, the choice circuit for preparing the possible choices, and the update circuit for evaluating the update to calculate the next state. Together, they form the state transition circuit for the model, which produces the next state S prime given the current state S. Now let's explore each part in detail. First, the guard function calculates the guard conditions. For example, if the current state S is 0, the flag for the first command G1 is set to 1. If S is 1, the flag for the second command G2 is set to 1. These calculations are replicated by controlled X gate shown on the right. The left gate in a box replicates the calculation of first guard by applying the X gate to the G1 qubit controlled by the state qubit S. The controlled gate is similar to a classical if statement, and the X gate is similar to a classical NOT gate. In this way, classical logics can be replicated using quantum versions of classical gate. Next, the choice function prepares probabilistic choices for each command. In the weather model, the first and second comments have 50-50% probability choices and 100% single choice, respectively. These choices are created using a rotation gate as shown on the right. The first gate in a box is control rotation gate to prepare the choices of the first comment. It modifies the choice qubit, CH, to encode a 50-50 probability when the first guard is 1. The second gate is control identity gate for second comment, but it essentially doesn't need to do anything as the choice qubit initially represents a 100% probability of being 0. By adjusting the rotation angle of the gate, you can replicate any probability distribution on the choice qubit. Finally, the update function calculates the next state based on the selected comment and probability choice. In the model, two updates of first comment update the next state to 0 and 1, respectively. These updates are implemented using control identity or X gate, where the control selects the comment and choice, and the identity or X gate sets the next state. The update circuit can be constructed like the guard circuit because it needs to translate classical logic into quantum gate. Similarly, you can translate more complex model into a transition circuit in the same way. For example, on the left, you can see a model with more complex expression and probabilities. The model is still broken down into guard, choice, and update functions, where the guard, choice, and updates can be any Boolean expression, any probability distribution, and any assignment expression, respectively. These functions are then translated into their respective circuits, the guard circuit, the choice circuit, and the update circuit, as shown on the right. As we saw earlier, each circuit performs the role of each corresponding function, forming the state transition circuit that produces the next state S prime and D prime, given the current state S and D. In summary, we can translate the model into a transition circuit using a three-step translation. Then by repeating the transition circuit and utilizing QA algorithm, you can perform probabilistic model checking on a quantum computer. You analyze our algorithm for the translation time on a classical computer, the execution time on a quantum computer, and the resource requirement. Translation time is another major concern as we directly translate the high-level input into quantum circuits. Because the size of the input is manageable, the translation process is not a bottleneck in the end-to-end process. In the next slide, I will explain the time complexity and resource requirements. First, we compare the time complexity of the classical and quantum approaches. We focus on comparing the statistical method because both are scalable and provide probabilistic answer with accuracy improving over time. For the analysis, you assume M is the model, T is the number of transitions, epsilon is the error bound. The result shows that our quantum approach is quadratically faster for the same accuracy. This comes from two factors. First, the single sampling cost is the same as in the classical approach because our translation keeps it proportional to the number of operations in the model. And second, QA achieves the same accuracy with quadratically fewer samples. This speedup is particularly beneficial for analyzing critical systems, which requires extremely small error bounds to prevent rare events. Next, we analyze the resource requirements of our quantum approach. To do this, we implemented our translation method in Qiskit and counted the number of qubits and gates in the translated circuit. We used case study from a benchmark shoot with state space and transitions ranging from 2 to 24 to 101 and 4 to 100 respectively. As a result, we found that the required qubits range from 1,000 to over 10,000, and the number of gates ranging from 100K to over 1,000K. While these requirements are not feasible with current quantum hardware, we are hopeful it will be available soon as companies like IBM and Google aim to build practical quantum computers in the near future. So far, I have explained how to use a quantum computer to perform probabilistic model checking. The paper includes additional details not covered in this talk, such as translation details, qubit optimizations, and quality proofs. Please refer to the paper for more detail. Thank you for your attention.
Question session?
Thank you for the very nice talk. given that amplitude estimation offers a quadratic speedup, whereas the runtime blowup of model checking is exponential, could you give an idea of the largest concrete problem sizes that become tractable under the quantum approach?
Could you please explain again what the exponential complexity comes from?
You showed earlier on the runtime slides, right, that the,
Yeah.
not on this slide, but earlier on in the talk when you first introduced the complexity of model checking.
Complexity of
Earlier than this, actually. Earlier, I believe. Yes, right around here, right? So, okay. I suppose I should ask a clarifying question. What is the time complexity that is required under the statistical approach to model checking here?
So
is it exponential in the state size, or is it polynomial in the state size, or?
So there are two approaches in which one is numerical approaches. They are exponential. In the numerical approach side, their complexity is exponential to the state space size, and the statistical approach side, their complexity is quadratic to the desired accuracy.
Okay, thank you for the answer. I might want to follow up with you after, but thank you.
Thank you.
Very nice talk. So you say your algorithm is quadratically faster than the classical one. What size of problem instance do you need for the quantum approach to be faster than the classical approach?
Actually, so you mean what size of problem can be accelerated in practice?
So I imagine that for small problem instances, the classical approach is still faster just because classical computers are very fast. But then at some point, this quadratic complexity will kick in. And I wonder, this quadratic improvement of the complexity will kick in. And I wonder, what's the size of the problem for which the quantum computer will be faster than the classical computer?
Actually, you don't have specific idea because it depends on the cost of single quantum gate. Because even if you have this asymptotic automatic that quadratically speed up over the same accuracy, but in practice we need to consider the single quantum gate, the cost of single quantum gate.
You can look that up in the manual.
Yeah, but I think that it depends on the quantum hardware. So.
Okay, that's fine.
Yeah,
thank you.
Yeah.
I would like to ask were there any interesting problems when applying quantum amplitude estimation to your algorithm? Because you also keep around all the previous states, not just the final one, I think. Right?
Could you speak again?
While running the transition system, you keep around not just the final state, but the previous ones as well. Did that have any effect on the quantum amplitude estimation algorithm? Did it work well? Did you need to fix anything?
No, you can use the general quantum amplitude estimation because we already encode we already encode the all result into the result qubit. So only thing we should do is just extracting the probability of the being true state in the result qubit. So you can extract this probability using just general quantum amplitude estimation.
Thank you.
Yeah.
Thank you for talking.
Yeah, thank you.
Yeah, we have our third talker today is a learn-based quantum optimizer.
Okay. Hi everyone, I'm Zikun Li. And today I'm going to introduce our work, CrabTree, a learning-based quantum circuit optimizer. So a quantum circuit is essentially a quantum program consisting of a set of qubits and a set of operations operating on those qubits, which are also referred to as gate. An example circuit is shown here. So ideally, the quantum devices run the quantum circuits perfectly. However, there are several issues with the quantum devices today. The first issue is that the gates are noisy, which means that the result of the computation could be incorrect. And the error rate of 2-qubit gates in today's superconducting devices could be around 1%. And the second issue is decoherence, which means that the qubits have a limited lifetime. So the number of gates that can be applied before the decoherence happens is limited. The issues in today's quantum devices motivates us to optimize the quantum circuits toward less number of gates and the lower circuit depths. So quantum circuit optimizations are performed by applying quantum circuit transformations. A circuit transformation is composed of two equivalent circuits that can replace each other. So here we show two example transformations. And in this example, we use these transformations to optimize the circuit below. Here we first apply the first transformation to change the order of some of the gates. And then we apply the second transformation that cancels all the H gates in the circuits. And finally, we get the optimized version of the circuit. There are several existing quantum circuit optimizers in two categories. The first category are rule-based quantum circuit optimizers. So this method involves some transformations that are manually designed by quantum experts. And they typically involve some fixed heuristics to apply those transformations. For example, an optimization path might be to apply transformation 1 followed by transformation 2, which means that the application of the transformation is not very flexible. In recent years, there's another line of work, which are search-based quantum circuit optimizers. So instead of manually designing the transformations, search-based methods can generate the transformations automatically. And they apply those transformations with search. So in Quartz, the authors use a greedy search-based method. And in Quetzal, the authors use a bin search, which is also greedy. And the search-based method generally achieve a better performance than the rule-based methods. However, one of the drawbacks of the greedy-based approaches is that they cannot fully utilize the cost-increasing transformations. Here's an example of how cost-increasing transformations may help us achieve a better performance. So as you can see in the figure, originally, the number of gates in the circuit is 8, and the depth of circuit is also 8. And we apply some transformation to it. So in the second step, we apply a cost-increasing transformations, which increases both the gate count and the circuit depth to 9. And finally, we can see that these cost-increasing transformations allow us to finally reduce both the gate count and the circuit depth to 7. This figure shows the optimization process of a circuit with two different sets of transformations. One includes cost-increasing transformations, the other does not. So when cost-increasing transformations are included, we can see that the best circuit we can achieve has 46 gates. While in contrast, when the cost-increasing transformations are included, the best circuit we can achieve has 36 gates. This is a very significant improvement. So these examples show that cost-increasing transformations are very important to the performance of the optimization. However, it's obvious that greedy-based approaches cannot utilize those transformations. The second drawback of search-based method is that they cannot navigate the large and planar optimization space. So this figure shows the number of steps we need to reduce the cost of starting from some random sample circuit in the search space of an original circuit. As you can see here, more than 50% of the circuit need at least 4 steps to reduce their cost. The number of circuits reached by the search grows exponentially with the search steps, which means that the search-based methods are not very scalable. So in light of these drawbacks, we propose Quack, a reinforcement learning-based quantum circuit optimizer, which replaces the greedy search in prior works with reinforcement learning. So Quack achieves up to 17% improvement over the current best existing method. There are 2 main reasons to employ reinforcement learning in this setting. So the first reason is that, in contrast to greedy-based method, reinforcement learning can better balance long-term and short-term rewards. And the second reason is that reinforcement learning balances exploitation and exploration, which means that once it recognizes a sequence of action that works really well, then it can learn to apply it to elsewhere without repeated exploration. And as shown in the figure below, a typical reinforcement learning problem defines a Markov chain, which is composed of 3 key components: a state, an action, and a reward. So applying an action on a certain state causes the state to transit to a new state. And meanwhile, a reward is generated in the environment. So now we formulate the quantum circuit optimization problem into a reinforcement learning problem. So first, a state is a quantum circuit in the optimization space of the original circuit we want to optimize. And an action is to apply a transformation at a certain location of the circuit. So in this paper, we managed to describe the location of a transformation by a gate. So we say that an action is to apply a transformation on a gate. And finally, the reward is the cost of the circuit before applying the transformation minus the cost of the circuit after applying the transformation. However, there are several challenges to apply reinforcement learning to quantum circuit optimization. The first challenge is that action spaces are very large and often varies. And the second challenge is that the state representations is complex. So we propose 2 techniques to address those challenges, which are action space decomposition and local state representation. I'll introduce these challenges and their solution in detail. So the first challenge is large and varying action space. For example, a transformation set in Quartz has around 8,000 transformations. If a circuit has 1,000 gates, then there are 8 million of possible actions. And if the number of gates in the circuit changes, the total number of actions also changes. However, common reinforcement learning algorithm only deals with a small and fixed action space. So to address this issue, we propose to decompose the action space into 2 subspaces, which are the gate subspace and the transformation subspace. So with this decomposition, to apply an action, we first select a gate from the gate subspace, and then we select a transformation from the transformation subspace. And then we apply this transformation and obtain a new circuit. So without this decomposition, we have to choose one action from millions of actions. In contrast, now we make 2 decisions in an action, where each each decision has a much smaller decision space. And since the transformation subspace is fixed, we can use existing reinforcement learning algorithms to learn to choose transformation. The second challenge is the complex state representation, that how we try to represent the state. A naive approach is to represent a whole circuit as a representation vector. However, this doesn't work very well in practice because the circuits have very different sizes. And for example, there are two circuits, C1 and C2. Suppose C1 has 10 gates and C2 has 1,000 gates. And it's obvious that the density of information in their vector representation are very different. This could lead to unstable training and weak generalization to unseen circuit sizes. So to address this issue, we propose to generate local state representation for the gates that include a fixed size neighbor area of the gate in the circuit instead of the whole circuit. This is based on a key insight, which is the locality of the transformations. A transformation typically involves only a small piece of subcircuit and only influences a small area. So when a gate is chosen, the best transformation to apply to the area is greatly guided by the local area of the gate instead of the whole circuit. That's why we use the local representation of a gate to guide the selection of transformation there. Now, based on these two insights, we propose the architecture of Quack. So first we have an input circuit. And then we have a gate representation generator, which generates a representation for each gate in the circuit. And then, based on these representations, the gate selectors select one of the gates. And the selected gate's representation is passed to the transformation selector, which selects a transformation to apply to that gate. And after the application, we get a new circuit. And we repeat this process to find an optimized circuit. I'm going to introduce the three components in detail in the following slides. So the gate representation generator is a graph neural network. We can take this C0 gate here as an example. So to generate the gate representation for the gate, the graph neural network gathers the information in its neighboring areas, layer by layer, just like this, like layer 1 and layer 2 and layer 3. And then the graph neural networks combine all this information in this neighbor area into a vector representation. And gate representation generator generates a representation for each gate. Now we have a representation for each gate in the circuit. The gate selector selects a gate based on their representations. It first predicts a value for each gate based on its representation. A higher value indicates that there are more optimization opportunities in the local area. And then the values are normalized into a probability distribution with a softmax function. And then a gate is sampled with the distribution. After we choose a gate, we pass its representation to the transformation selector. So the transformation selector outputs a probability distribution over all the transformations. From this probability distribution, we sample a transformation and apply it to the circuit. Now we have the overall architecture of Quack, which consists of 3 neural networks. So the question is, how do we train them? In Quack, we train the 3 neural networks jointly with the PPO algorithm in the following way. So we first collect some data that composed of a circuit, the selected gate, selected transformation, and a reward. And then we use this data to update to generate policy loss and value loss based on the PPO algorithm. And we use these losses, we backpropagate them to the model to update the weights. And please refer to our paper for more details. And here are many other challenges that we solved in CRAW, but they are not included here due to time limit. And please refer to our paper for the challenges and techniques to address them. Here I just list a few of them, which are hierarchical advantage estimation that help us localize advantage estimation, and pre-training and fine-tuning for better generalization, and policy-guided search for more efficient optimization. We conducted extensive evaluation to compare CRAW with the existing systems. As shown in the figure, CRAW outperforms all the baseline systems on both gate count and CNOT count under the IBM gate set. So the results under the non-gate set and in circuit depths are not shown here, but they have a similar result. CRAW outperforms all the baseline systems. These results show the effectiveness of CRAW's reinforcement learning-based method in quantum circuit optimization. So in summary, we propose CRAW a reinforcement learning-based quantum circuit optimizers. Thank you for your time and attention. I'd like to take any questions.
Question?
Very nice talk. How big is your training set, and where did you get it from?
Okay, so as shown here in our training methodology, the training set is actually collected during the runtime. It's like, so reinforcement learning is a method that it has some self-exploration in the environment, and then it collects data, and we use this data to train the neural network.
How big is the training set then?
I think you mean how many circuits we used during the training. Yeah, I think, as I remember, it should be a small number. It's like 10 circuits. Yeah. So we select those very representative circuits and put them into the training set and let the reinforcement learning algorithm to self-explore.
Thanks for the very cool talk. Could you comment on how the challenges of using RL to optimize quantum circuits compares to the challenges of using RL to super optimize classical assembly programs?
Yeah, I think that's a very good question. So I think actually the method applied in this work can also be applied to some other questions, other problems that can be like abstract into the form like there is a DAG, and you can apply some graph transformations to optimize this DAG. So I think the assembly optimization problem we might also be able to use this methodology to optimize this assembly optimization problem. Yeah, that's my insight, but I'm not sure if I understand correctly what the assembly optimization problem is. Yeah.
Thank you.
Thank you.
Could you compare the execution time of your method against with some existing SOTA methods such as Quartz or Quasar?
Okay, so I think the question is to compare the time we use with other baselines. So in evaluation, we give the same time budget for all the baselines. However, we also found that even if we increase the time budget for all the other baselines, they cannot achieve a better performance. This is because search-based methods are not very scalable. So the search space grows exponentially. All right, thank you.
Okay, that works. Hi everyone, the final quantum talk of the day, so let's get through it. Another 20 minutes and then you're free to go to lunch. I'm Jasper and I'm going to present synthetic, fast and versatile quantum circuit synthesis, which is a work I did together with Anouk, Benjamin and Martin. Now, if you've got this far into this quantum talks, I'm assuming that you already know what a qubit is. If not, let me remind you, of course, qubit is the quantum equivalent of a bit, either 0, 1, or any linear combination of both. What is important for this talk, though, is that you can also represent it as a vector. And this vector representation we will use in our circuit synthesis method. Now, for 2 qubits, this generalizes pretty straightforwardly. Instead of 2 states, you have 4 states, and your vector representation consists now of 4 numbers, all complex. Now, in quantum computers, you of course want to apply operations on these input states, and the way we do that is using operators. So operators are simple functions that go from one state to the next state. In this example, we have k qubits, and then your input representation is of the form c2 to the k. As a simple example, the Hadamard gate, when applied to the 0 state, gives a combination of the 0 and 1 state, and applied to the 1 state, the same, but with a minus sign. Now, what is important about these operations is that they are linear, and thus we can represent them much more easily with a matrix. And the way to read these matrices is essentially, if you look at the first column of the Hadamard gate, that is the output that you get when you input the 0 state. The second column is when you input the 1 state. So we can simply represent the operations or the operators, what they do on input states, by a matrix multiplication, multiplying them with the vector representation. Now, we're not quite there yet because we cannot tell our quantum computer to implement arbitrary operators. Why not? Well, quantum computers only have a limited gate set that they can natively execute. A very common gate set is the Clifford plus T gate set, which consists of these gates. The Hadamard gate I already showed you. Then you also have the S and the T gates, and finally the C naught or the CX gate that is applied to 2 qubits. So these are the only gates that we can natively execute, and this of course leads to circuit synthesis, which means that we need to convert our operators into circuits that we can actually execute on quantum computers. So for example, suppose we have this very simple operator. We make it into a circuit that first apply a Hadamard gates, then a C0 gate, and then another Hadamard gate on the second qubit. So the problem statement we get here is, given an operator specification U, synthesize an efficient circuit. Now, this is not exactly what we wanted to tackle with synthetic. As mentioned in the title, we wanted to be as versatile as possible, and there are actually problem statements in circuit synthesis that are not captured by this statement. And there are 2 aspects that are still missing here. The first one is approximate synthesis. So because you only have a finite gate sets, there are infinitely many operators for which you cannot find a finite circuit that implements this operator. So the way to approach this is to approximately implement them, allowing for some distance that is not 0, but can be up to epsilon, which is some number. For those that are interested, this distance metric is usually of the form related to this, which is the Hilbert-Smith distance. But what it is exactly isn't important for this talk. So adding this first element to our problem statement, we're now not only given an operator specification U, but also a maximum distance epsilon. The second missing component is partial specification. And what does partial specification mean? Well, some applications in quantum computing do not require you to specify each entry in your matrix specification. So when you do full specification, that means that your entire matrix, your entire operator is specified, and each element in this matrix is important. However, you can also have isometries, where you only care about specific columns and you do not care about other columns. When does this happen? Well, for example, in state preparation, you know that your input qubits are in the 0 states, and therefore you do not care what your operator would do if you had any other input states than the 0 state, which corresponds to this matrix here. The reason that you want to do this instead of full specification is, one, it's easier to specify this as a user, but 2, it's also more efficient to implement. Here, a very trivial example, of course, but even though our CCX gate is not the identity gate, our isometry here can be simply implemented using identity. Of course, not very practical, but in this case, it's like this. Of course, you can also have just full partial specification, which means that you don't have just rows and columns that are specified or not specified. You can have arbitrary elements that are underspecified. And a use case here is relative phase operators, which you can see when you apply Boolean matrices or Boolean operators to your circuit. So Boolean operators is the CCX gate, which only consists of 0 and 1s. And relative phase operators essentially mean that you want zeros in the same position, but you do not really care if it's 1 minus 1i minus I that is in these non-zero positions. And oftentimes you can replace these Boolean operators with their relative counterpart while maintaining basically your entire algorithm structure. Even though these relative phase operators have a more efficient implementation. So how do we specify this? Well, we specify this with 2 matrices instead of 1. One is our original specification U. Another one is a Boolean matrix, and this Boolean matrix basically indicates which elements you want to specify and which elements remain underspecified. And if you want to give this into your computer, you basically say U on the question marks 1 minus 1 doesn't matter. Our algorithm doesn't look at this. So we get our final problem statements. Given an operator specification um and a maximum distance epsilon, synthesize an efficient circuit. Now, how can we approach this? Well, the problem is that prior work looks at very specific gate sets, looks at very specific exact synthesis or approximate synthesis, so we couldn't really use the optimizations that they used in their algorithms in this very generic problem statement. But what we did notice is that simulated annealing is actually a pretty generic, simple algorithm that works perfectly for this problem statement. In simulated annealing, if you don't know what it is, you essentially keep perturbing your input circuit or your circuit to get closer and closer to your specification until you finally got it. So what does this mean? Well, here I've written a very simple implementation of simulated annealing. You first have some initial circuit C and some parameters, or epsilon and our specification. You check if your distance is smaller than epsilon. If so, you found your implementation. If not, you mutate your circuit, and then you probabilistically accept your new circuit or not. When you accept it, well, you definitely accept it if your distance becomes smaller, because that means that you're getting closer. But you also want to accept it if it's only slightly worse than your original circuit, because essentially you want to get rid of these local minima that you can get stuck in, and that's why you also want to get out of there. What makes simulated annealing also very applicable in this situation is that it's very parallelizable. So it's very scalable to more qubits or more gates this way. There are 2 things that we have to specify still in this algorithm. One is this distance function, and for that I'm going to refer to the paper because those are messy details that we don't really care about here. The other one is the mutation that we do, and the mutation is very simple. Suppose we have a circuit C. We either apply deletion of a gate, we swap a gate, or we add a gate. Those are the 3 operations allowed, and this way you can basically form your mutations. Now, the problem with simulated annealing is that it doesn't lead to very efficient circuits. Like these random perturbations, there are lots. If we apply this straight like this, it leads to crazy simple optimizations that you can do in your output circuit that you really want to get rid of. So what we do is a very simple simplification algorithm. We could also have used Qual or any other resynthesis tool, but we noticed that this simple tool was good enough. And what does it do? Well, given our output circuit that implements our operator, we simply swap or replace gates that are replaceable. In this case, 2 Heidelberg gates after each other are just an identity gate. Then we swap the T and the S gate because they are swappable, so why not? And then finally, again, we replace the 2 T gates to a single S gate because that works. And then we keep doing this until we finally get our optimized circuit in the end. Okay, so let's take a look. Synthetic is what our algorithm is called. We support any finite gate set, any optimization objective, incomplete specification, exact synthesis, approximate synthesis. And I hear you thinking, sure, you're very generic, but this cannot be efficient, right? You're certainly, you lose some efficiency, you lose some speeds in order to implement all these specific applications. Well, let's take a look. And here in the presentation, I'm going to compare to one other baseline that we compared against, which optimizes for Clifford plus T depth, which is basically the amount of T gates you have to execute sequentially. And they only do exact synthesis. And what do we find? Well, it's over the board a bit, quite a lot, from no speed up to 10 to the power 4 speed up. But on average, or the median, is 2 orders of magnitude speed up that we actually reach with synthetic. So even though we have a very simple algorithm, we seem to be outperforming this baseline. And what this plot doesn't show is that in 30% of the cases, Giorgio times out, while we can still find a circuit. What it also doesn't show that in 80% of our circuits that we tested on, we find more efficient circuits than Giorgio finds, and in the other 20% we find the same circuit that they do. Okay, we also want to apply synthetic in practice on actual circuits, so we applied it on 5 operators that we found are relatively interesting in practice. And we find that either synthetic in a reasonable amount of time, at most 8 hours, can find more efficient circuits than prior work or prior best effort things. So what we did for this previous best is we looked through papers, we tried to apply several algorithms to see which one works best, and then reported this. And with synthetic, we can simply do this all automatically, and we either reduce the number of OOPSLA, which is the number of helper qubits that you need to implement the specification, or the T-depth of the circuit. So in conclusion, we looked at this problem statement, which is very generic with the operator specification UM and a maximum distance epsilon. We used simulated annealing to solve it, and we found that in practice we get more efficient circuits. Thank you.
Question session?
Thank you for the talk, very cool. So it seems from your specification that you can recompute M from U, is that correct? And if so, why do you actually need M in your spec?
Yeah, so that's a very good question. So basically the reason that I showed this U and M is because that's the way we implemented in code. Like in code, you cannot specify question marks. So in the code, how this works is that these question marks are basically zeros, and then this M we use additionally to show like, yeah, these zeros are zeros, but you can do whatever you want there. So essentially, that's why I showed this with question marks. But yeah, if you are able to work with question marks in in your code, then you would be totally fine, and then you wouldn't need M.
Very nice. Your examples at the end, I think they have like 4 qubits or 5 thereabouts. What's actually the kind of the limit that your tool can handle in terms of number of qubits?
Yeah, so like it depends both on number of qubits and number of gates in your circuits. So we found that for 4 qubits, which is the use case we look at most, we can get to around 30 gates at most for like a reasonable amount of time you would need to implement this. From 7 qubits, you get out of memory errors because we store these entire matrices which become very, very large. And for 5 and 6 qubits, basically you get to very low gate counts that you can implement. So I think the largest I implemented I tried at some point is like 3 or 4 gates for 6 qubits and 5 or 6 or 7 gates with 5 qubits.
Is this stuff very parallelizable so that like GPUs might have a chance to do better here?
It's very parallelizable in the sense that you can do simulated annealing, like you can do multiple runs at the same time. I don't think, because GPUs would help if you can do this matrix multiplications that we do for like getting the circuit that is within one simulated annealing one, and I think there it could also help if you implement these matrix multiplications on GPUs as well, yeah.
Thank you for the great talk. Have you explored whether there are cases where simulated annealing performs worse than on average? Like, have you done any worst case analysis? Are there surprising outcomes?
So we didn't do worst case analysis, but you can kind of see here in this plot already that like there are some cases where we seemingly not outperform prior work. So there does seem to be cases where synthetic doesn't really directly like find it more efficiently than prior work. And I looked into this and I was wondering like how does this happen? And I couldn't really find a reason why it wouldn't work for one case or another case. One interesting thing I noted though is that the more qubits we had, the better our approach became compared to prior work. So essentially for one qubit, I looked into approximate synthesis for one qubit mainly, and they were the same compared to prior work. Well, the more qubits like 2, 3, 4, you get better and better and better. And the reason for this is because of these distance functions that we use. And for one qubit, it doesn't really give that much information. So this distance function shortly is based on this Hilbert-Schmidt distance. And as you can see, because we only apply one new gate in each thing, we can only change parts of your part of the matrix. Because some elements will stay the same if you only apply a Hadamard gate to the third qubit or something. But if you have only one qubit, then basically every new gate that you apply changes the entire matrix. So then I found that in this case, this distance metric doesn't work that well. And like, yeah, that's one case where synthetic kind of fails in some sense.
That's very interesting. Thank you.
So I have a question. So
Yes.
Have you actually tried other gate set? Because I guess you're only showing one gate set that is
Yes.
the gate set, but how about other gate sets?
So in the presentation, I indeed only included Clifford plus T gate set. In the paper, we also compare against a tool that can also handle other gate sets. And there we see basically the same kind of performance improvements as we had compared to the Giorgio baseline. So yeah, we did do this, and we did see that in this case we also get a significant improvement.
I have another question. It's like this. Okay, so because you are actually giving a unitary and then to synthesize the circuits for you. I understand. But I guess based on my experience, I guess the most need for you are giving a unitary and then going to synthesize the really circuits. Basically, you are dealing with some of this Hamiltonian simulation that simulate a very large like a system that you actually expect you have 100 qubits. So have you actually thought about how you actually can parallelize the computation of, let's say your unitary is it's talking about 100 qubits?
So how to extend this approach to more than 5 or 6 qubits? Yeah, this is very hard. Like there are several things that you would need to do to make this even remotely applicable to this setting. Is one, you have to get a more efficient, not implementation, but way to represent these states, because full matrix specification doesn't work when you don't work with 100 qubits. That's way outside of the scope. So this you would somehow have to change that. For partial specification, this is very hard because these question marks are in random positions, so you would somehow need to do this more appropriately, and I couldn't find a way to do this. A second problem when you go to 100 qubits or more is that the amount of options that you have for mutations are getting extremely, are just getting too big to basically handle. So I think for when you want to go to 100 qubits, synthetic is not the best approach because this random search is just not going to work. There are too many options. Either what you do is you try to decompose in smaller and smaller circuit. So you decompose your 100 qubits operation into maybe 5 qubit operations, each one that you don't know how to implement, but it works to synthesize it like this. And then you use synthetic to do these 5 qubit ones. The problem there is what do you use to get from 100 to 5? And there are several algorithms that can do this, but they're just not very efficient. They generate a circuit like the Kitaev, I always forget the name, the Kitaev-Kolomov algorithm does this, but it's just very, very inefficient to do something like this. So it's kind of a trade-off how you want to approach this for larger operators.
Thank you, thank you.
Oh.
Craig is giving the talk.
Great, thank you. As he said, I'm Craig. Thank you for coming. I'm here to talk about Cedar, a new authorization language that we developed at AWS. This is joint work with a whole bunch of awesome people that you see on this slide. But to start it off, what is authorization? Well, authorization is the problem of determining who can do what in a multi-user application. Authorization is a critical component of pretty much any modern web application that you'd want to build nowadays. And for example, it's about who is allowed to comment on a doc or who's allowed to view a payroll stub. Why is this a hard problem? Well, certainly the theory is known. You can go to the literature and you could read all about role-based or attribute-based or relation-based access control. The theory's been pretty well developed, in fact. But that doesn't mean that it's easy to implement permissions in your application. As an example, let's take Tiny To Do, a toy example application that allows users and teams to create, manage, and share task lists. So we have users that can be organized into teams, which can be nested, and we have task lists, which have metadata, like a name and an owner, as well as actual data, a list of tasks. Tiny To Do is a web application, and its server-side or back-end code is written in Python. So here's the handler for the getList operation. It does about what you'd expect. We query the database and we return appropriate data. For the purposes of this talk, the most interesting part is the access check, because not everyone in the universe should be allowed to get data about all possible lists. So how should we implement this access check? Well, the most natural way, and how it would normally be done in web applications today, is by writing the logic right here in the request handler in Python. And this works, but it has a few problems. First of all, it's hard to write. We had to take all of the conditions under which access should be allowed and invert them to get the conditions under which we need to return this access denied error. We also had to get the nesting right, which is not always trivial in all cases. In fact, errors in authorization logic like this formed 4 of the top 25 common security weaknesses, or CWEs, last year. Another reason that this way of doing things is suboptimal is that it's hard to audit. If you need to go and make sure that your application has done permissions correctly, or if you need to ask questions like who has access to what, you have to comb through the entire back-end code of your application. Likewise, it's hard to maintain permissions that are written this way. If you need to make a change to your application's permissions posture, you probably need to make the same change across many different request handlers, each of which will have similar but not identical code, because it's likely that slightly different rules apply to different operations. What should we do instead? Well, we should delegate the authorization decision to a dedicated authorization engine, which evaluates authorization policies written in an authorization language. This fixes a lot of the shortcomings of the previous approach. First of all, it's easier to write permissions this way. We're writing in a dedicated DSL that understands authorization concepts like permit and forbid, or like resource and principal. It's also easier to audit and maintain permissions that are written this way, because they're all stored in a single central location. If you need to check that your permissions are correct or make any changes, you only have to do that in one place, and you don't have to touch the rest of the back-end code of your application. So that's why we developed Cedar, a new authorization language focused on centralized decision-making. Cedar is at the core of 2 different AWS services, Verified Permissions and Verified Access, which have customers in many different industries, including healthcare, telecom, and asset management. But Cedar is also open source on GitHub. And as a result, it's been picked up by a number of startups, including StrongDM and Common Fate, who have built their entire core products around the Cedar authorization language. But what is unique about Cedar? Why a new authorization language? After all, there's already plenty of authorization languages that exist. Well, we identified 5 desirable properties of an authorization language, and we claim that Cedar provides a new way to balance these criteria, a new point in the design space that we think makes a lot of sense, and in particular has a focus on analyzability, which was not a focus of many previous authorization languages. Another thing that's unique about Cedar is that it is the first authorization language built from the ground up with high assurance in mind. We used an approach that we call verification-guided development, and which we wrote a paper on that was actually already presented at FSE 2024 last summer. It talks about how we use formal verification and differential testing to ensure that our implementation of Cedar is correct and obeys important security properties. If you are interested in hearing about that part of the work, I highly recommend you go check out the FSE paper. But in the rest of this talk, I'm going to focus instead on what is Cedar and how do we use Cedar. So like I said, 5 desirable characteristics of an authorization language. We have ergonomics. Policies should be easy to read and write, even by non-experts. We have expressiveness. It should be possible to write authorization policies in all 3 of the major paradigms that we see in the literature: role-based, attribute-based, and relation-based access control. We have safety. We want to be able to catch policy authoring mistakes and prevent them before they cause any harm. We have performance. We want to evaluate requests quickly. And finally, we have analyzability. We want to be able to build sound policy analysis tools that enable us to reason about the permissions posture of our application and whether it respects important security invariants. But the reason that these properties are challenging is that they are often in tension with each other. And in particular, the 4 properties on the right are often in tension with the one on the left, which is expressiveness. So when we were designing Cedar, we generally favored the 4 properties on the right at the expense of expressiveness. We just wanted to make sure Cedar was expressive enough to express policies in the 3 major paradigms: RBAC, ABAC, and REBAC. In particular, we drew a line in the sand around analyzability. We wanted to ensure we had a sound and complete encoding of Cedar policy semantics into decidable SMT formulas. And the word decidable is very important there. It's not just that we have a sound and complete encoding of Cedar policy semantics into SMT formulas generically, but into the decidable fragment of SMT, which ensures that we get strong and consistent performance even from our solver queries. So let's talk about each of these 5 properties, starting with expressiveness and ergonomics. Here's a Cedar policy. You already saw it a few slides ago. This policy says that anyone is allowed to take the get list action on any resource if they are in that resource's readers or editors group. The policy has 3 parts. First, we have the effect, which is either permit or forbid. Then we have the scope, which has optional constraints on the group membership or identity for the principal action and resource. So this policy has a constraint on action. So it only applies to requests where the action is exactly get list. But it does not have constraints on principal or resource, which means that so far, the policy applies to all principals and all resources. And then finally, we have conditions, which are Boolean expressions written in the Cedar language and prefixed by either when or unless, and they further constrain when the policy applies. Cedar policies are evaluated over an entity hierarchy. So in Cedar, principals, actions, and resources are all entities, and entities can be members of other entities, including recursively. So here we have a bunch of user entities that are members of team entities, which are themselves members of other team entities. And entities also have attributes, which have a name and then a type, a value of any type in the Cedar type system. So in our case, list entities have attributes like name of type string and owner of type user. So that's actually a reference to another entity in the hierarchy. Cedar requests are conceptually 3 tuples, principal, action, resource. So this request asks whether Kesha, the principal, can take the action get list on the resource list123. And the request will be allowed if it satisfies at least 1 permit and no forbid policies. So this request will be allowed because resource is list123, so resource.readers is the temp team, and Kesha is indeed in the temp team. But if we asked whether Emma is allowed to take the same action, that would be denied. And this is an example of an important security property of Cedar, which is that if a request matches no permit and no forbid policies, if it matches no policies at all, then it will be denied. Similar to how Neha was describing this morning for a different permission system. On the other hand, if we add back in the 2 other policies that we saw several slides ago and reissue the request with Emma, now it will be allowed because of the second policy that says anyone in the admin team is allowed to take any action on any resource. We could also ask whether Andrew is allowed to take the create list action, and you might think that that would be allowed because Andrew is also in the admin team, and anyone in the admin team is allowed to take any action on any resource. However, this request would actually be denied because of the 3rd policy, which forbids anyone in the temp team from taking the create list action. And this illustrates another important security property of Cedar, which is that forbid always overrides permit. We have formal semantics for Cedar policies and how they are evaluated in the paper. So if you're interested, you can go see the paper for that. But let's move on and talk about another two properties of authorization languages, which is safety and analyzability. Cedar has a policy validator, which is essentially performs type checking. So you can declare, you can have a schema in the Cedar schema format, which declares important type level information about your application and the entities in it. And then you can validate your policies against this schema in order to catch mistakes and prevent runtime errors. So let's validate this policy. We see that the policy refers to an action called getList. So we look that up in the schema, and sure enough, there's a declaration for an action called getList, so that's valid. And furthermore, the schema tells us what principal and resource types are allowed to be used with that action. So here we see that the principal type must be user, and the resource type must be list for this action. That allows us to type check occurrences of principal and resource elsewhere in the policy. So when we see resource.readers or resource.editors, we know that resource must be of type list, and then we can see from the schema that entities of type list do have attributes called readers and editors, so that's valid. And it also tells us the type of those attributes, which allows us to type check uses of those attributes. So when we see principal in, first of all, we know that principal must be of type user from the action declaration. And then the schema also tells us that entities of type user are allowed to be in entities of type team, which makes this a valid use of the Cedar in operator, because one of the valid type signatures for the Cedar in operator says that if users are allowed to be in teams, you're also allowed to use in with user in set of team. In general, our policy validation algorithm detects improper entity relationships, unrecognized attributes, actions, and entity types, illegal operations at the type level, pretty much what you would expect from a type checking algorithm. It's a pretty standard type checking algorithm. It does have some features that you might find interesting, like flow-sensitive capability tracking. So it turns out that in Cedar schemas, you're actually allowed to declare that some attributes are optional and may or may not be present at runtime. And then Cedar policy validation actually ensures that you will never get runtime errors resulting from trying to access an attribute, an optional attribute, that did not exist at runtime. This works because validation will actually ensure that your policy must check for the existence of the attribute before it is allowed to access the attribute's value. This works via flow-sensitive capability tracking, a feature of our type system that was partially inspired by TypeScript. We then proved a soundness theorem that says that if validation succeeds, policy evaluation will exhibit no runtime type errors, or indeed a few other kinds of errors like attribute does not exist. Formal statements of this, including of our theorems and the proofs of them, are all in the paper. But in addition to validation, we also have policy analysis to reason about the semantic content of policies and answer universal questions about the behavior of policies on all possible inputs. This works via our sound and complete encoding into decidable SMT formulas. So one universal question we might be interested in is equivalence. Do two policies or two sets of policies produce the same decision on all possible inputs? This might come up in a refactoring setting. So suppose I wrote the two policies on the left. The first one says that anyone is allowed to take the create list or get own list actions. And the second one says that anyone on the intern team is actually not allowed to take the create list action. So suppose that for whatever reason, I wanted to refactor this into a single policy that had the same effect. I could do the refactoring and then invoke policy analysis, which will lower both of these policy sets into SMT formulas. And then I can ask the SMT solver, do they produce the same decision on all inputs? And of course, the SMT solver will tell me, no, they're not equivalent. And it will give me a counterexample for, in this case, that if Aaron is an intern and tries to take the get own list action, that'll produce an allow on the left and a deny on the right. So I can fix the problem and then run it back through the SMT solver, and it will tell me that they're equivalent. Formalisms for exactly how this compilation to SMT works and how we use solvers is all in the paper as well. Finally, let's talk about performance. So Cedar is written in Rust, which is one reason why it is very fast. It evaluates typical inputs in under 10 microseconds. That's microseconds, not milliseconds. And Cedar's runtime is also strictly polynomially bounded, which is in stark contrast to a lot of other authorization languages which are Turing complete and therefore have no strict bounds on their authorization time. We compared Cedar against two different open source authorization engines, Rego as well as OpenFGA, which is based on the Google Zanzibar system. And we compared all three of these engines on three different applications, Tiny To Do, which you've been seeing in this talk, as well as 2 applications that we borrowed from the OpenFGA examples library, one that encodes the GitHub permissions model and one that encodes the Google Drive permissions model. And we rewrote all 3 of these applications' permission systems into Cedar, Rego, and OpenFGA for this comparison. So here are the performance results. On these graphs, Cedar is in green, OpenFGA is in orange, and Rego is in blue. So you can see that as inputs get bigger along the x-axis, Cedar's performance stays strong and consistent. It's just hugging the x-axis there. You also see both solid lines and dashed lines on these graphs. The solid lines represent median performance, and the dashed lines represent the 99th percentile performance, or P99. You can see that even Cedar's P99 is strong and consistent. In conclusion, Cedar provides expressive, fast, safe, and analyzable authorization. It is open source on GitHub. Come check us out. And we also have a website where you can find a playground, tutorials on how to use Cedar. Last but not least, we are hiring applied scientists to work on Cedar. So if that's you, or you think it might be you, or you're just interested in talking about what that might look like, come find me after or email me at this address. Thanks, and I'm happy to take questions.
Questions? Then there's a mic in the middle.
Thank you for the presentation. I was actually today at the keynote at 9 a.m. where Neha was talking about using Daphne to do, I think, similar things. Does Cedar have like any interop capabilities with Daphne, or is it like a completely separate, are they like responsible for completely separate things?
So Cedar, there are a couple answers. First of all, Cedar is a completely different system than the IAM system that Neha was talking about at the keynote. The IAM system that she was talking about is used by AWS to control access to its own principles and resources. And Cedar is sort of a reimagined version of it with lessons learned, and also that allows you to control access to your own application's resources. So it's much more generic in that sense. But the other answer that I'll give to your question is that we do have a formalization of Cedar in Lean, and that we proved theorems about it. And that's discussed a lot more in the FSE paper that I referenced early on in the talk.
Awesome. Do you plan on replacing the entire like Daphne workflow with Cedar in the future, or?
We have no plans to do that.
Okay, thank you.
Hi, really cool talk. At lunch, I heard Armando talk about program synthesis, and now I come here and there's a set solver, there's these properties that we want. So have you thought about probably leveraging the set solver not only to prove that certain properties always hold or never hold or something like that, but also actually to help people write these things? So maybe I have a permission that I'm not sure how to write, I'll leave a hole and maybe the set solver can help me. Have you given that any thought?
Yeah, I haven't given that very much thought, but it does sound like a great idea. I think that one of the problems you're going to run into is coming up with a good enough spec for what the policy should do that is constraining the sat solver enough to like come up with the right answer, right? We've found that people have a hard time writing specifications about their authorization system. It's not a way that people are generally used to thinking. In this community, we do it a lot, but like engineers in the world, it's sometimes hard to express the invariance that you're thinking about.
Okay, oh, thank you.
As we go to the last question, maybe Ethan, you can set up.
Really cool talk. I had a kind of a vague question, which is like you described this as being a new, particularly well-informed point in the design space, which makes sense. Do you see like the future of programming language design as being just continuing to learn lessons and carve out better and better sets of points in the design space of possible DSLs? Or is there like a future in which there's maybe a continuum? Like, I don't know. It's kind of a vague question, but I'm curious to hear your thoughts.
I mean, so I think that definitely we are going to continue to learn lessons and try to design DSLs that strike better and better balances. But I also think that that's a pretty small vision for what the entire future of programming languages will be. I think that we also are going to continue to see big ideas and programming languages that look nothing like the languages we've seen before. You know, this community has come up with a lot of really radical ideas for what languages should look like, and I hope we see more of that in the future too.
Cool, thanks.
All right, perfect timing. Let's thank Craig one more time. Our next talk is about CoerSpace, and Ethan will be giving the talk.
All right. Good. All right. Hey everyone, today I'm Ethan, and today I'm going to be talking about CoerSpace, which is a domain-specific language for color programming. Before I get into the contents of the paper, it's probably a good idea for me to talk about the field of color science and what we term the term color program to mean. In very broad terms, color science is a study of human color perception and cognition. Applications are wide, and they include graphics, historical preservation, photography, color reproduction, photogrammetry, among many, many others. And in our paper, we specifically define color programs as programs that manipulate visible spectrum and color data. Examples of color programs include color blindness simulation, white balance algorithms, otherwise known as chromatic adaptation transforms, and digital simulations of pigment mixing. Unfortunately, the current ecosystem for writing color programs kind of sucks. Color programs are particularly prone to uncaught errors. Bugs in user code can easily pass compiler or interpreter scrutiny, and these bugs often require domain-specific knowledge to avoid and manifest themselves in rather subtle ways. As such, logic bugs often remain uncaught both by compilers and by users. So if you've used any photo editing software or painting software before, you've probably seen this slider here, or some variation of it anyways. It's an sRGB slider, or an RGB slider. It uses just the amount of red, green, and blue primary used to display a color. And you've also likely seen HSV sliders as well. Instead of adjusting amounts of R, G, and B, you instead adjust amounts of hue, saturation, and brightness. So what's interesting here is that the HSV value below and the RGB value above are numerically different, but they actually represent the same color. So HSV and RGB are different encodings of color, and in color science, we refer to these encodings as color spaces. And a lot of people are only really aware of these two color spaces. However, there are a truly massive amount of color spaces out there, and these are the only ones that I could list. These are only the ones I could list off the top of my head. So, and on top of that, failure to keep track of the color space of image data can lead to subtle bugs. Take image compositing as an example. Let's say I want to place this poorly green screen kiwi near Pasadena City Hall. However, the kiwi image is encoded in the ProPhoto RGB space, while the photo of Pasadena City Hall is encoded in the sRGB color space. In order to composite these two images together, programmers should convert the kiwi photo from ProPhoto RGB space to sRGB space first, as seen below. But nothing's really stopping programmers from skipping the color space conversion entirely. Even though the image of Pasadena City Hall is encoded in sRGB and the kiwi is encoded in ProPhoto RGB, this segment of Python code runs without issue. In Python, these images are represented simply as arrays. As such, if the dimensions of the two images match, and they do after some transformations, Python libraries take no issue with executing the buggy code. The incorrect implementation outputs the following image. So as we know, performing arithmetic on color data of different color spaces is physically meaningless. It's no op. However, the produced output is still approximately correct. For reference, this is the output of the correct implementation. The difference between the two is rather subtle. Without a direct comparison, the error is pretty hard to notice, and if you wrote buggy compositing code, you might not have noticed that you had made a mistake at all. So let's move on to a much more simple example. Let's say you have a color, like the one on the left, and you want to find a corresponding color that is of the same chromaticity but half as bright. A naive programmer may simply divide the RGB values in half, but this would actually be incorrect. In reality, having luminance is not equivalent to having RGB values, because RGB is a nonlinear color space. A linear increase in an RGB value does not correspond to a linear increase in luminance. This is not a very obvious fact. Without domain-specific knowledge of the sRGB standard, it's easy to mishandle color data entirely. So in summary, color programming is incredibly error-prone. Programmers need to keep track of the color space of data manually, and domain-specific knowledge is required to avoid errors. Errors that the programmer does make results in subtle data corruptions, which makes debugging color programs particularly difficult. The fundamental cause of all of this grief is that colors in image data are often represented as just array data. Therefore, array operations that are mathematically permissible but physically meaningless are run without issue. The other motivation behind CoerSpace is performance optimization. It's easy to forget just how large image data is. Take these parrots, for example. This full HD image, 1920 by 1080p, takes up 5.93 megabytes uncompressed. And full 1 minute, 60 frames per second full HD video takes up even more space, 21 gigabytes to be precise. With such large input sizes, even minor optimizations yield pretty tangible runtime benefits. Luckily, there's a potential solution. We can view image data as tensor data, as people already do in the machine learning field. And this image can simply be represented as a 1080 by 1920 by 3 tensor of float 32 values. And since there's a large body of work on tensor algebra optimization due to the field's relevance to AML, you know, they're swimming with money. If we compile color programs down to a tensor algebra intermediate representation, we can effectively piggyback off techniques developed in this field to optimize our color programs too. Finally, let's get into talking about CoerSpace. So CoerSpace is a Python metaprogramming library. Users write Python programs using CallStore library, and we type check those user programs. If they do type check, we compile them to Onyx, which we are using as a tensor algebra intermediate representation. We then use equality saturation to optimize these Onyx drafts, and the resulting Onyx drafts after equality saturation can be compiled further or run with arbitrary inputs using Onyx runtime. I want to first focus on the compilation stage. So the goal of the compilation stage is to use types to statically enforce color program correctness and to reduce the amount of boilerplate code a user needs to write. As discussed earlier, a major cause of color programming errors is the fact that color data is often represented as raw arrays with no information about encoding. In CoerSpace, object types are a cross-product between the physical type of the data and the dimension of the data. We use the term physical type here to refer to the type of color data that is represented by an object. Here's a graph of the physical types CoerSpace currently supports. The nodes of the graph represent physical types. So it's important to note that CoerSpace's physical types do not only include different color spaces like sRGB and OBRGB, and we also support data in the form of light reflectance and absorption spectral data. Yeah. So the edges of this physical type graph here represent valid conversions. For example, the edge highlighted in orange represents conversion from LMS space to XYZ space. And that's also represented in the equation on the left. Color spaces are often defined in relation to other established color spaces, hence the web-like structure of this graph. Let's take a look at how our type system can alleviate programmer burden while preventing common color programming issues. The example program above calculates the sRGB value of a spectral distribution of light. The line highlighted initializes an object of the light spectrum, and this expression tells CoerSpace to cast the light spectrum to sRGB space. So CoerSpace only type checks the casting between physical types if a path exists from the source type to the destination type. In our case, there does exist a string of transformations that we can utilize to convert a light spectrum to an sRGB value, hence the program type checks. Behind the scenes, conversions from light spectrum to LMS to XYZ to sRGB are chained together to perform the casting without the user needing to worry. So in this example here, a programmer is attempting to calculate the light spectrum corresponding to an LMS value. LMS is a 3-dimensional color space, while light spectrum is a high-dimensional color space. Therefore, there cannot really exist a transformation from LMS values to light spectra. Such an operation is severely underdetermined. In fact, there are an infinite number of light spectra that correspond to a single LMS value. Therefore, the type checker rightfully rejects this code snippet. For our next example, let's say you're trying to do some simple arithmetic between two colors. In this case, just simple interpolation. Seen here, but the problem is that they're represented in different color spaces. This is a mistake, the same mistake that the faulty image compositing implementation made from earlier. But luckily for us, our type system specifies that arithmetic may only occur between colors of the same color space. Therefore, this bug does not pass the type checker's scrutiny. The luminance example for earlier is also remedied by our compiler. And recall that in many color spaces, there is some form of nonlinearity, like an sRGB. So when a user specifies that they would like to do any arithmetic on color data, our compiler performs said arithmetic in linear space, with the caveat of perceptual spaces, but that's a bit outside the scope of today's talk. So our succinct CoerSpace code above is equivalent to the NumPy code below. In the NumPy code, the nonlinearity of the sRGB color space must first be removed. Then the user-specified operation occurs. Then the nonlinearity must be reapplied. In CoerSpace, this code is actually all handled for you behind the scenes. It's worth noting that not all color spaces are nonlinear, and that different color spaces are nonlinear in different ways. Therefore, our compiler makes use of the CoerSpace information of the object to correctly apply and remove nonlinearity. Next, I want to briefly touch upon our optimization process. As mentioned before, we can represent color programs in the language of tensor algebra. We can therefore use techniques that have been proven to work on tensor algebra, like equality saturation, on our color programs. We choose to use equality saturation as our optimization technique of choice in this paper, as our programming model is quite high level. Due to CoerSpace's quite strict type rules, users can't directly write the optimal implementations of many color science algorithms. Therefore, we have opted to use an expensive but effective state-of-the-art tensor algebra p-pole optimization method. But also, please note that CoerSpace is not bound to equality saturation. Compiling down to a tensor IR enables us to make use of many tensor algebra-specific optimization techniques. So take the following example code. This is code for a naive implementation of color blindness simulation. And this code is compiled down to an Onyx graph, which we are using as a tensor algebra IR. Then the graph is serialized and passed into egg, an equality saturation framework. Egg uses our custom rewrite rules and cost function to search for an optimal Onyx graph. This Onyx graph is then passed to Onyx runtime for constant folding. Egg is capable of performing constant folding, but since color science data is so massive, and since Egg operates on string inputs, it's not very economical for us to perform constant folding using Egg. Instead, we modify our cost function such that the operations that are pre-computable are assigned a cost of 0. This allows our implementation of equality saturation to effectively still utilize constant folding. Finally, we arrive at our optimized Onyx graph. It's much more succinct and much faster to run. So we benchmark CoerSpace against a handful of programs designed to test the entire gamut of CoerSpace's current feature set. We first measured compilation and optimization time by benchmark program. In our experience, compilation and optimization time overheads were consistently insignificant across all programs. We also ran our benchmark programs with varying input sizes on both our optimized and unoptimized executables. We found a geomean speed of around 15% across all programs. And in the best case scenario, we found around a 44% speed up. So we also tested our benchmark CoerSpace against existing Python solutions, including Numba and color science. But what is it? Sorry. My screen died here. We found that CoerSpace was consistently faster than existing solutions, but this is almost certainly just due to our difference in technology stack. CoerSpace isn't bound by the limitations of the Python interpreter. Therefore, we don't have to consider that overhead. In fact, we even benchmark our unoptimized CoerSpace executable against the other existing solutions. Rather, here we prove that CoerSpace is able to guarantee type soundness and correctness guarantees without extra cost to the user. Here's a list of sources that I used during this presentation, and here are some useful links, including our GitHub repositories and Python package index links as well. And down there are a list of emails, but the one that you should probably pay attention to the most is this one, because that's where you will be sending all your internship opportunities. Thank you very much.
Wait, stay for questions.
Sorry. Yep.
Any questions?
Hi, I'm Adrian Sampson from Cornell. This is a very nice talk. This is very cool. I was just curious if you encountered any precision issues with the optimization. So there's like rewrites that would be true on the reals, but this is a fixed point representation. Do any problems come out?
No, it was a floating point.
Floating point,
and yes, we did encounter instability issues. We solved that by removing a few equality saturation rules that had to do with the power, manipulating power operators. We found empirically that solved most of our issues.
Thank you.
Thank you for the talk. It's a really cool project. I think the verifications has been much needed. My question is there any plan to allow people to write CoerSpace code in a language that has a type system expressive enough to not require a meta compiler?
None yet, though we're certainly open to the idea.
Cool, thank you.
Any other questions?
Hi, I'm Jesse. I'm curious about the use of equality saturation. In particular, you showed sort of unoptimized and optimized, but I'm curious if you just removed that step, like how crucial was that step to your final performance results?
Well, you mean unoptimized versus optimized executables or ONNX graphs? If we removed equality saturation alone? Oh, yeah, it's pretty crucial. Pretty much all of our speedup comes from equality saturation because it turns out that constant folding with just ONNX runtime can't really be done unless you reorder the operators in a way that's palatable to ONNX runtime.
Okay, thank you.
All right, I have a question about the language and type system. So the examples you showed, I gather that expressions have sort of concrete types in terms of the color spaces. Do you ever have programs where you want a polymorphism? Is there polymorphism in the, like parametric polymorphism in the language and type checker where I could write something that works for any color space, or are there no such functions that work for any color space?
No such functions.
There's
yet.
no such functions. Oh,
Sorry.
okay. That is interesting. Okay. Any other question? Okay, great. Well, let's thank Ethan one more time. Thank you. We are going to hang out for a couple of minutes to be on the synchronized schedule. So we'll just wait a couple of minutes since we're a little early.
Okay.
We don't want to start early.
Okay.
Because other people.
Okay. This is hard.
And when you get 13 minutes in, I'll let you know.
20 minutes.
It's 20 minutes total. The intent is 15 minutes or so talk.
I think it's between 15 or 20.
Okay.
Okay.
When you get to 13, I'll say 2, but you can take that however you
Okay. Okay. Okay.
Can you please confirm that you do not want to stream the talk? Because it
okay, it's okay. You can stream. You want to stream or not?
I don't care. It's just that we have on the presenter form that you do not want to stream this.
Okay. No, so you don't. So should I start?
No, let's wait a minute.
Oh, wait a minute. Okay.
Does this work? Yeah,
Yep.
okay.
All right, so for our next talk, Paul will be telling us about the expressive power of some languages for static variability.
Yeah, thank you for the introduction, and I'm happy to see that some people still remain on the sunny afternoon. I want to start with a user story. So meet Alice and Bob. They are C++ developers, and they had a hard day at work, so they're going to a diner to relax a bit. They enter and they're shown this menu where they can create their own sandwiches. So this is like a menu sheet that offers you different ways to configure your sandwich, for example, different kinds of bread or cheeses or sauces. And they wanted to relax, but Bob is eerily reminded of his work. And yeah, Alice has noticed this really resembles variability in their code base. And they're C++ developers, so they're facing C preprocessor annotations all day. So this is an example from the text editors within the code base. So, and you see C++ code annotated with C preprocessor statements. So we are mixing two languages, the normal C code, and in blue, and proceeding with these hashtags, the C preprocessor annotations. And depending on how you define these flags, so how a user configures their code, you end up with different C programs, or C++ programs in this case. So in case of a and depending on whether Microsoft Windows is the platform, you get different calls for your operating system. So yeah, and now that we think about it, it's not actually just sandwiches or code. There's like many domains, maybe like software, hardware, cyber-physical systems that are subject to variability, where we need tons of ways to configure our systems for the user. Most prominently also the Linux kernel, which is based on C and C preprocessor and offers like over 5,000 configuration options. So there's a huge amount of variability here. So the question is, how can we model and describe variability, not just for one of these systems or for one particular programming language, but for all of these kinds of domains? So to give you like an idea of where we want to go with this work, so all of you should probably be familiar with the idea of computation, and we're typically using programming languages to implement computation. So name your favorite programming language, Java, Haskell, you name it. And the semantics, or like the specification of our programs, can be given in terms of Turing machines, the lambda calculus. So this is the kind of formalism we use to say what a program is and what's not a program. So for static variability, we just saw we can use the C preprocessor, we can use aspect-oriented programming like in the previous talk, or sandwich menus. So what's it that we can put in the bottom here? So we want to find like a formal specification for variability across these domains. And there's actually a candidate out there. In the introduction of their own paper, they write, we're like the lambda calculus of variation, and it's called the choice calculus. It's very small. It has just two constructs. The first one is data, so we have some kind of tree, like an abstract syntax tree. And the second one is a choice, which offers us some configuration options. So as an example, let's consider we want to encode a menu for sandwiches, where we have always bread, maybe salad, always cheese, either tofu or meat, and any combination of sauces. So in choice calculus, we could write this down. Oh, where's my cursor? We could write this down in this way. We have at the root of our expression the bread, and the bread has 4 children. In this tree, we have a choice between salad or nothing. So we can say we have salad or we don't have salad. We always have cheese. So that's a data child with no children. We have a choice between the patty as being tofu or meat, and we can choose between any combination of sauces. And the semantics then is that we can configure all choices to end up with an expression without choices. So given a configuration, which is a function that tells us for each of these features, salad, patty, sauce, a value which we want to use, we can end up with, for example, this sandwich with salad, cheese, tofu, and ketchup. But it's actually not just choice calculus. There's a whole bunch of formal languages used by different research groups for different analysis, for different problems. And this is just some of the languages I found that have been used in practice. So the question is, how do these languages relate? Do they describe the same thing? Can we transfer research results from one language to the other? if I want to write a new variational analysis or formalize it, prove some properties, which language is the easiest to use for that purpose. So what we do is we want to first see what's the semantics. So what do they describe? Do they describe the same thing? So we want to depict what's the semantics of static software variability. So the idea here is that the semantics of an expression is a function that takes a configuration as input, resolves all variability, and gives us a variant. So in terms of our sandwich example, an expression must encode, like a cookbook, all the information we need to compose our sandwich, the ingredients to do so, and then a user can give us a configuration. The semantics is someone like the cook, who then prepares the final variant, a single sandwich, and a very particular one. So actually, we don't have the semantics of just one language. We want to compare expressions. So we dealt with 2 of these boxes. We want to have a semantics of 2 expressions. So how can we compare them? And the basic idea is translation, like building compilers. So the question is, can we translate the expression on the top to the expression on the bottom, and the configurations as well, because these can also be different kinds of data or formats, such that variants in the end are equal. So can I produce the same variants in both expressions, and vice versa? So based on that, we formulate a criterion for expressiveness. So the intuition is that the language can express everything another language can express when we say that this language is at least as expressive, which is a common notion also in the literature. So formally, this means for every expression in the second language, I get an expression in the first language that's semantically equivalent. And we can prove this by building a correct compiler. So if we compile M to L, we show that for every expression, we can find another expression. So given our world of languages used throughout the literature, somehow looks like this. We now want to relate them, draw some arrows into this picture. And the first languages we want to compare for this purpose is the choice calculus. We introduce a new family of language called the n-ary choice calculus, which means every choice has exactly n alternatives. So you can loosely think of this with another intuition for these languages as languages where you have only if expressions. So the choice calculus then on the bottom left is a language where I have any number of elif branches for each choice. N-ary choice calculus has a fixed amount of elif branches, and binary choice calculus on the top center then is a language with only if-else statements. And we then introduce these blue arrows. These are compilers. So these are proofs that a compiler exists from one language to another. And we show that like translating these if and else languages can be done via this language family to an arbitrary degree. We then also relate the binary choice calculus at the top with algebraic decision trees, which is another language which wasn't actually used to model variability until very recently. So this was a language introduced for game theory or some other algorithmic problems. We also compare these languages with option calculus on the top right. So this is a new language we introduced to capture what's the semantics of just if-then statements, because that's frequently used in variational analysis, but never was really formalized. So as you might guess, an if-then statement can always be expressed with if and else, but not the other way around. And finally, there's feature structure trees. I don't have time to talk about these in detail, but this is kind of a modular variability language. We have different modules, and then you can compose them. So not annotating a single tree, but composing the modules. So the part of this relative kind of expressiveness, where we compare the languages by translating, we're also interested in these classical notions of soundness and completeness, and especially completeness is like an absolute measure of expressiveness. Can we express every element our semantic domain? So formally, we say for every non-empty and finite set of variants or set of sandwiches, we want to find an expression. We want to be able to build an expression that does exactly that. And in the world of software engineering, this is typically known as differencing. In this case, n-way differencing, because we have n trees of input data. We want to find the similarities and differences in one expression. Soundness is the converse property as usual. So we want to express only variational trees. So from an expression, we want to be able to find the element in the semantic domain. And we can prove this by showing that all configurations can be enumerated. So we can go to the sandwich dinner, to the restaurant, get all the menus, and just make all the possible configurations on a sheet of paper. So proving soundness and completeness for these languages is actually a bit intricate and complicated, so we use a trick. And you probably know this trick. It's a language called clone and own. It's a common practice in software engineering, unfortunately, where you just duplicate your code to achieve the same result. And this is also a common language used at pizza restaurants. So this is a pizza restaurant from Pasadena. And they just list every single pizza available with lots of duplicate ingredients. So onions appears like 10 times on this sheet of paper. And you could also have one variational expression, like the sandwich diner. But pizza places like to do it like this. So and for this language, just listing all the different variants, it's very easy to prove soundness and completeness. And it's also rather easy to relate to the other languages. So we can then connect some circles, translate clone and own to these other languages if possible, and then can start to derive completeness for free for the other expressions. So the observation here is if one language is complete, and I can translate this to another language, so there's a more expressive language, then this other language must also be complete. So completeness flows along these arrows, and every reachable language will also be complete. So we find that there's this island on the left side, this chunk in the graph, where all languages are complete, the right ones are incomplete. This requires a separate proof, but also is hinted at by us not being able to traverse to the right. And conversely, soundness goes in the opposite direction. So we're lucky, everything is sound, so this means all these languages can be used to describe software variability. So we can conclude here that choice calculus could indeed be seen as a lambda calculus of variation. And so could be algebraic decision trees and clone and own. And we find at least 3 different classes of expressiveness, the complete languages, the incomplete languages, and also the ones on the right cannot be translated into each other. But there's maybe more questions arising here. So if there's multiple complete languages, are these equally good? And if there's different classes of expressiveness, and there's complete languages and incomplete languages, why should I care about incomplete languages? So regarding complete languages, are they equally useful? So let's take this expression from the beginning. If I could translate this to algebraic decision trees or clone and own, I get a combinatorial explosion. That's a well-known problem if you have code duplication and clone and own development. So now we have to list every variant, like in the pizza place. So no, not all languages are equally useful. Sharing of subterms is important. And for the second question, what's the value of incomplete languages? So we know choice calculus is complete. So when looking at our example, everything should be fine. But indeed, in fact, there's this weird empty value. So we can encode like options where we say we can have salad or we don't have salad. We can do this with options, but this requires this empty value, which is context sensitive, depends on our sandwich language or whatever else we're configuring. We can also encode it without these neutral values, but again, this requires duplication, which is annoying. And actually, in the incomplete language of just choices, so just this if-then language, we can avoid these drawbacks because we can encode these optional values, but we cannot express alternatives or other constraints, so that's making this language incomplete. So we conclude that you should probably use both, and that's also what's happened typically in practice, but not in these formal languages. So combining both kinds of expressions is what we recommend. So all of this is formalized in ACTA, every theorem, every definition, every language, every proof. We also provide some tutorials if you want to integrate your own language or translations. And the nice thing is, because this is intuitionistic logic, every proof comes indeed as an executable compiler. So we really have to show that everything works. So you can run the code, translate data sets, for example, and I invite you to have a look at our GitHub repository. So in summary, we witnessed some software developers having troubles with variability in the code. We present a formal framework for comparing the semantics of variability languages. We applied our formal framework to a range of existing formal languages to chart this part of the map of existing languages, and whether they're complete or incomplete. And we implemented everything in ACTA. So please have a look, and thank you for your attention.
Any questions to the microphone?
Hello, this was a really cool talk. I was wondering if your framework is able to compare languages that have different kinds of constraints on choices. Like if you had like a sandwich that says like I can only have cheese if I don't have tofu, or something like you can have new choices if you have one other kind?
Yeah, that's a very good question. So in this realm of software variability, software configuration, that's actually like two concerns. One's implementing variability like the languages here do, and then formulating constraints and lots of dependencies. You can integrate this into the languages as well, and there's some like more advanced dialects that do so. So for example, you could, in the C preprocessor, like the practical language, you could like write a huge formula on your macro. If this is selected and this dependency is satisfied, so this would be a naive encoding, and otherwise there's like models for externally encoding any dependencies, checking these, and then using only legal configurations. So in the dyna, this would be like an employee that checks whether the customer filling out the thing would be fine, and only then handing it to the kitchen. Thanks.
Thanks. I really like this talk. So my question is, you have this idea of these complete languages and these incomplete languages, and you say that there are some cases in which the complete ones can express things a little more simply and easily. I guess maybe that's not the best way to start my question. Maybe my question really is, you have a way to translate different variability languages into semantics. Do you have a similar way, or do you think there could be a similar way of translating specifications or like the kinds of variants you would be interested in a particular setting into a semantic objective? Or so you could say maybe this language is complete for this particular kind of variance or this particular set of sandwiches, and whether that would be useful.
Yeah, that's also a good question. So yeah, let me go back to this map. So we have thought of, and I mean also one of the reviewers asked this concern, yeah, you found like one semantic domain, and for this it's complete, but what about these languages on the right? Maybe there's better semantic domains. And there's indeed some syntactic properties, for example, of feature structure trees that make them incomplete, but it's not like that's an unreasonable reason. So that's a choice, a design decision they made for some good purpose. So one could say, let's constrain the semantic domain even more to like account for specific edge cases. And yeah, you could do that. So this is a very loose definition, like the broadest we could think of, that still matches some of the languages out there. Yeah. I hope this answers your question.
Sure, yeah. Thank you.
Thanks.
So you mentioned, we want to be on the complete side, and clone and own is obviously bad, but then you didn't tell us which one is best. Was that on purpose, or is there just no one best?
So the three complete languages we found is choice calculus, algebraic decision trees, and clone and own. But both algebraic decision trees and clone and own have this blow up, so use choice calculus.
Use choice calculus. Yeah. All right. Great conclusion. All right, let's thank Paul one more time. All right, for our last talk of the session, we will hear from Ji Feng. He will tell us about Quack, inference for Python.
Sorry about that. Let me adjust the display.
It's a nice bird.
Okay. So good afternoon, everyone. Today, I'm here to present my master's research on Quack, quick attribute-centric type inference for Python. So Python is one of the most favorite programming languages since 2018, surpassing longtime favorites such as Java and C. However, unlike these languages, Python is dynamically typed, which facilitates rapid prototyping and makes it particularly popular in fields such as data science and web development. However, with the rise of Python, we also see the rise of the disadvantages of dynamic typing, such as these pesky runtime type errors, which you may be familiar with. In contrast, static types enable more meaningful static analysis, error checks, and refactoring passes, Thus, in 2014, PEP 484 introduced Python type annotations, which are not checked by Python itself, but are used by IDEs and static type checkers to check the code before it runs. However, despite the advantages of Python static type annotations, only a tiny proportion of Python code is actually annotated. This 2020 study estimated only about 4% of Python code is actually annotated. The clear advantage of type annotations, but the apparent reluctance of developers to add them, has led to the development of several type inference tools that aim to reduce developers' burden. A good type inference tool should output as many type annotations as possible, achieving high coverage. In addition, its predictions should be correct, achieving high accuracy. Furthermore, it should be performant and should not run in too much time. Static type inference methods utilize rule-based approaches, data flow analysis, and heuristics to create and solve typing constraints. They aim for correctness and achieve high accuracy with simple types in limited contexts. Machine learning-based methods use natural language queues with various machine learning models. They can handle the complexities of Python and can improve coverage. However, they face out-of-distribution generalization challenges and cannot guarantee type correctness. Furthermore, they may incur significant performance issues, such as immense requirements for computation and energy, especially for large language model-based methods. Thus, finding a balance between coverage, accuracy, and performance remains challenging. Let me present an example that existing approaches struggle with. In the code on the left, the global function maximize has the parameter points and the return value element. The industrial static type inference tool PyType does not make predictions for points and predicts elements to be the trivial any. The state-of-the-art academic static type inference tool Stray does not make predictions for both points and element. The state-of-the-art non-LLM machine learning-based type inference method HiTyper predicts points to be tuple, which is technically correct, but is over-constrained, as points could also be lists. In addition, it does not predict the type parameters of tuple. Furthermore, it predicts element to be string, which is wrong. Last, the recent LLM-based type inference method type T5 predicts points to be list, which is also over-constrained, as it could also be tuple, and it does not predict lists type parameters. It does make the correct prediction for elements, though. However, this is a good example that showcases the power of our type inference tool, Quack. So Quack determines the type of variables based on the attributes that are accessed on them. In the global function maximize, we can observe that the parameter points accesses the iter method for iteration on line 10 and the getItem method for indexing on line 9. Thus, it has the attribute set iter, getItem. Based on this attribute set, the parameter points could be something like a list, a tuple, etc., and Python's typing module defines a sequence particle that covers all such cases. And our method, based on this attribute set, can correctly predict that points should be of class sequence. Now, sequence is a container class with a type parameter t. And Quack then can predict it to be the user-defined class point. We'll get to container type parameter prediction later, but for now, sequence of point is the most generic correct type here. Furthermore, for the return value, the case is a little more simple. The return value calls its method maximize on line 11. Thus, it has the attribute set maximize. If the user-defined class point is the only class within this context providing this attribute, then element should be annotized with point. Quack also correctly predicts its type to be point based on the attribute set. In the upcoming slides, I will first introduce Quack's core approach before showcasing the highlights of our evaluation and discussing remaining challenges to be addressed. First, I will start with Quack's core approach. So given an attribute set for an expression, Quack first predicts its class. Quack chooses its class from a class query database, which Quack constructs as follows. The class query database includes built-in classes such as int and list, protocols from the Python standard library such as the sequence, classes from imported external modules, as well as user-defined class such as the point. Then, given an attribute set, Quack must select the best class that provides those attributes. For example, in the example that we've showcased before, many classes such as typing point sequence, typing point mutable sequence, as well as a built-in list, all provide the attributes iter and getItem. To rank these candidate classes, Quack uses information retrieval techniques similar to what a search engine does. Specifically, it uses the BM25 ranking function, a standard information retrieval heuristic, to rank candidate classes. The score of a candidate class is as follows. So in this formula, we consider all the attributes in the attribute set, the IDFs or rarity of those attributes on all classes, the frequency of attributes within that candidate class, which is either 0 or 1, depending on whether the attribute is absent or present, as well as the candidate class's length in relation to the average class length. So with the BM25 ranking function, we can prioritize rare attributes and the smallest class that satisfies an attribute set. And if the predicted class is a container like sequence, Quack then predicts its type parameters. In the example that we've discussed before, Quack predicts the class of the parameter points to be sequence. Now, sequence is a container class with a type parameter t. To infer t, Quack first determines the semantics of t, which we represent with the relation set value of, iter target of. This means that t has the types of the values stored in a sequence object and the types of the elements iterated over a sequence object. In the source code, we notice that element is a value that is being accessed on points, and p stores the value that is being iterated over points. Thus, based on t semantics, we can conclude that it has the attributes of element and the attributes of p, leading to the attribute set of maximize. Based on this attribute set, we can predict the class of t to be point, which is not a container, so we conclude that the type of t is also point. We fill in the type variable t and predict the type of parameter point to be sequence of point. In this process of predicting container type parameters, we have used the concept of relations. First of all, we use relations to model the semantics of container type parameters. For example, in dict kv, the relation set of the parameter k includes key of and iter target of, suggesting that k has the types of the key stored in a dict and the types of the elements iterated over a dict. In comparison, the relation set of v includes value of, suggesting that v stores the types of the values in a dict. In addition, we also use relations to associate potential container expressions with semantically related expressions when we analyze source code. For example, given the for loop for x and y, we record that y is iter target of x. And given the indexing expression x indexed by y, we record that y is key of x. And x indexed by y is value of x. This procedure allows us to recursively predict container type parameters. This finishes our introduction of Quack's core approach. We will now discuss our evaluation. To evaluate Quack, we compare it against state-of-the-art baselines, such as state-of-the-art non-LLM methods, including Stray, a static type inference method, and HiTyper, a machine learning-based type inference method. We also compare against the recent LLM type inference method, type T5. We use popular real-world Python projects in our evaluation and use MyPy, a type checker, to check the correctness of the predicted type annotations to measure our accuracy. We also compare it against the ground truth type annotations on the typed benchmarks in our paper, but we are not talking about that now. So we compare Quack against the non-LLM benchmarks in terms of coverage in this graph. Stray is the blue bar, HiTyper is the red bar, and Quack is the yellow bar. When compared, Quack and HiTyper are similar in coverage as measured by the number of non-trivial type annotations which are not none, which are not object, and which are not any, with Quack further leading on several benchmarks, such as Peewee, Seaborn, Sphinx, and Workzog. Regarding accuracy, Quack also consistently outperforms Stray and HiTyper across most benchmarks. Though Stray does achieve high accuracy on some benchmarks, it makes much fewer type predictions and fails to make any predictions for a lot of the benchmarks. Regarding performance, Quack also vastly outperforms Stray and HighHyper on almost all benchmarks with an average runtime reduction of 15 times. These data show that Quack excels at balancing coverage, accuracy, and performance. When compared against type T5, the LLM-based method shown by the green bars, though type T5 predicts 1.9 times more non-trivial type predictions on average, it also incurs a significant runtime cost, with type T5 being nearly 2 orders of magnitude slower than Quack. Thus, we can still say that Quack excels at balancing coverage, accuracy, and performance. Now, let's compare Quack against the baselines in predicting container type parameters. So the annotation list of int, where we have the type parameter filled in, is much more useful than simply the class list, where we don't have the type parameter. When compared against the non-LLM methods, Quack predicts many more type parameters on a majority of the benchmarks. And it also does so at a higher overall accuracy. This demonstrates the effectiveness of Quack's approach to predicting container type parameters. However, what's interesting is that when compared to type T5, Quack predicts a higher number of parameterized containers on the untyped benchmarks, while type T5 does better on the typed benchmarks. This shows that there is a clear distribution shift affecting type T5, depending on the presence of type annotations in type T5's pre-training data. We used a two-tailed t-test to analyze the difference and found out that there was no significant difference for Quack, while there was a highly significant difference for type T5. This shows that when compared to type T5, Quack is significantly more consistent in predicting container type parameters. Finally, I will discuss a remaining challenge. Quack fails when there are too few, too unspecific attributes. For example, in this function, the parameter s is only involved in 2 multiplication operations. Its attribute set only includes 1 attribute mul, implementing multiplication, and occurs in both numeric and sequence types. Given the single attribute, it is challenging for Quack to decide that s should be stir, a conclusion that can only be reached by considering the natural language cues, such as the function name, as well as the names of the variables. Thus, a meaningful research direction would be to include Quack as part of a hybrid LLM symbolic method. This enables using LLMs to leverage natural language cues. On the other hand, including Quack also has the potential to improve performance and mitigate the training data bias when compared against a pure LLM-based method. So this concludes our introduction of Quack, quick attribute-centric type inference for Python. We hope you enjoy the talk and feel free to scan the QR code to access our paper and our GitHub repository. Thank you, and I look forward to any questions.
Questions to the mic, please.
Hi, Arjun from Northeastern. Thank you for the talk. It's very cool work. Python is like worse than you described. What I'm thinking of is things like, it's not just classes, but people do things like just use dictionaries and pass them around. And if you're very good about typing your code, you might sort of use things like type dict. I understand that this is like beyond the scope of what you're doing, but any thoughts about that?
Yes, so I guess the modeling for a typed dict could follow a similar pattern for the modeling of things like container type parameters. So for container type parameters, we defined relations which associated the semantics of the type parameters with expressions in the code. And for things like typed dict, we may have similar syntactically defined rules that says, well, we have a dict-like expression and we access certain fields on it, especially using string literals as the keys, we may record those keys as potential members of the dict. So this may be a future research direction that may help in predicting things like type dict.
Cool. So one very quick question. So BM25 has a bunch of parameters that you can sort of play with. Did you do anything with that?
Not at the moment. So I just used the default reproduction package. So.
Okay.
but I could explore that in the future.
Hi, this is really cool. I like the structural approach that you took here, but in lots of Python code, it's common to narrow types based on like the results of is instance checks or identity or equality checks. Are you doing any of that? Because like if I compare a type equal to, or if I compare a value equal to some other value, it's not really useful to know whether it supports a Dunder-EQ method, but rather what the right-hand side is so that I can narrow appropriately.
Yes, so what you mentioned is actually a future research direction that I'm considering. So one of the future research directions that I mentioned is, adding Quack onto an LLM. Another research direction is adding the framework of Quack onto something like MyPy, which supports the type narrowing, the branch-sensitive type prediction that you've discussed. So it's definitely a future research direction that I'm considering.
Cool. And then I also really like the way that you're querying attributes on like a database of known classes. Have you considered using that to like detect typos and method names and things like that, where a type is close except for a very near method?
So I guess that is a very interesting direction of future work, and I see potential with that being integrated with the LLM symbolic type inference method that I suggested, because sometimes those typos, we could leverage the capability of large language model to understand natural language cues in that scenario.
Thank you.
You're welcome.
Any more from the audience?
I have one question.
Okay.
So I was wondering, is there, did you look at the soundness of your type inference? Can there be cases where you're losing the soundness of the inference?
So right now, what I'm doing is a simple information retrieval technique. So I'm not explicitly considering the soundness in this scenario, but it works quite well in practice, as we have demonstrated in our experimental evaluation. But as I just suggested, a future direction of work would be to put this thing on top of MyPy. So in this case, after we make a prediction, we can use MyPy to check it. And that would bring greater soundness guarantees.
Okay, thank you. Nice one.
Okay, let's thank Jifeng. And that brings us to the end of the session. So enjoy the break.
to testing everything, everywhere, all at once. Well, that's what it was. That's why I named it like that. And we have 5 papers today. The first paper is going to be from CMU. Oh, with Karina, nice.
Yep.
And is going to look at Rust as one of the subjects for testing. So please, go ahead.
All right. All right, thank you very much for the introduction. Sorry, let me move the mic up a little bit. Yeah, there you go. I'll be giving a talk on CrabTree, which is a Rust API testing tool. For those of you who stayed at this hotel, it's not the soap. All right, so let's back up and talk about Rust. So Rust is gaining a lot of traction in important software, such as operating systems like Linux. Windows has components. Google Fuchsia is using Rust. In the cloud, Lambda, S3, and a variety of services are now being written or rewritten in Rust. And in the user space, browsers like Firefox use it in the core rendering engine. And with all these big, important pieces of software getting written and rewritten in Rust, there's a demand for testing tools. Now, let's start off what's worth testing in Rust. So Rust is a memory-safe language, which means when a piece of Rust code type checks, its memory safety is assured. There are no bugs like use after free or double free or other kinds of memory bugs. This is achieved through its type system, which restricts the pointers. In particular, every piece of memory is owned by one unique variable, and then every mutability and parallelism are controlled. However, this restriction is sometimes a little too restrictive, and so a feature of Rust is this unsafe keyword, which allows for unchecked pointer use within the code block that's marked with it. However, if you use this, there's a risk that the bugs that are prevented by the type system shall return, or may return. Given that unsafe code is not something to be easily used, a common design pattern in Rust is to wrap unsafe code in library APIs. Here's how it looks like. So in the library, experts write the library implementation using unsafe code, making a lot of optimizations by leveraging unsafe, while the programmer writes mostly safe code. And the average users who use the libraries don't need to use unsafe. Instead, they make API calls into the library to leverage high-performance APIs. Now, given this setup of wrapping unsafe code in libraries, it's very important to test the API thoroughly. Otherwise, the unintended side effects of unsafe code may leak out to the programmer side, and the bugs may ensue. Let me give you an example of an API sequence that triggers a particular bug. This is a real library called bitvec, which implements a bit vector. And here, a strange or rather usual sequence of API calls triggers a bug. So if you make a bit vector with initial capacity 0, and then push a 1 bit onto the bit vector, this causes a memory allocation, and immediately converts the bit vector into another type called bit box. Doing so immediately after the memory allocation causes a use after free because one of the piece of memory is hanging out. And as you can see, the programmer did not write any unsafe code. But because the library's APIs internally contain unsafe, we just got a memory bug. Now, suppose you wanted to trigger these kinds of bugs. Suppose you want to synthesize API sequences like those. There's a history of tools that synthesize API tests. These tools take in a set of APIs, F1 for FM, a template, and through a variety of techniques like graph search or SAT solving, generate API call sequences, and then run these sequences using a bug definition to determine whether a bug has been hit or not. However, we did some sample of Rust code from Crates.io, and it shows that a lot of the existing synthesizers cannot handle real Rust code. These are libraries that are from the top of Crates.io, but existing tools like Rolf don't handle traits and higher order functions, which are like the quarter of all trait APIs. CyRust is another tool that does handles even less features. So, for example, it doesn't fuzz inputs, and half of the libraries were parsers. So if you don't mutate the inputs, well, your testing can be limited. Furthermore, CyRust scalability is an issue. So 3/4 of library APIs at the top of crates.io had 100 plus APIs, and CyRust handles around 20. We propose CrabTree, which is the tool that handles traits, higher functions, does input mutation, and then tests around APIs in the hundreds of API sets. We achieve this with a scalable test synthesis algorithm that allows us to handle a large API set, and a technique for synthesizing higher function calls. Now, we know that there's some interesting interesting synergy between fuzzing and synthesis, but due to time restrictions, I'll skip over this. Now, to understand why CyRust is not very scalable, it helps to think of the test synthesis problem as a tree search problem. So at the root of the tree, there's an empty program. And each edge, you descend the tree with an API call. Now, you might call F1 and then F2, and then the node that you reach by calling F1 and F2, by descending those two edges, is the program, F1, F2. In this conception, each level of the tree is a set of programs of that length. So for that level 2, that's length 2 programs. CyRust, in this conception, implements BFS, that is breadth first search. Now, it enumerates line by line, going from enumerating everything of length 1, length 2, length 3, length 4, and so on. And this has two primary issues. First of all, this set of APIs of a particular length, this is a fairly large set. So if you enumerate everything in that set, you're going to time out. CyRust with, let's say 50 APIs will reach about maybe line 3 before timing out. Furthermore, because CyRust internally uses SAT solving, this becomes cost prohibitive, and CyRust solving will time out. They will fail to synthesize any tests. Even though there's all this compute and struggle going in, there's a very small fraction of tests actually contribute to testing or coverage performance. That is represented by the blue shard, very small, and in practice it's a little smaller, even smaller than that. We propose CrabTree, which is a heuristic-guided DFS algorithm for synthesis of tests. And the idea here is to synthesize longer programs selectively. We prioritize tests that produce line and branch coverage, that is dynamic coverage information, and produce new types that have not been seen before. So using DFS, CyRust synthesizes line 1, and then given a subset of line 1 that CyRust classifies as interesting, it synthesizes length 2, length 3, and sometimes it veers off course, but because it's a heuristics guided DFS, it would return back to the more interesting subset of programs using a priority queue. Now let's see how this could be used to synthesize the bug. Here in line 1, we see that this program is prioritized because it generates a new type, that's the bit vector type, and the new coverage because you're running a library API. Then we make a mutable reference to that bit vector. Now, mutable reference is a primitive operation, so this does not create a new type, a new coverage, but it creates a new type. And using that mutable reference, we do a push. We push 1 bit onto the vector. This creates a new coverage because this is a library API, but it doesn't create any new type. And finally, we synthesize the conversion into bitbox, and then the bug is hit. Observe here that the heuristics are complementary. So the type and coverage, both are needed. In some cases, like line 2, if you only have coverage, you won't, that will be deprioritized. If you only have type, line 3 will be deprioritized. So these are complementary heuristics. Now, let's go on to traits and higher order functions. So traits and higher order functions, traits in Rust, I won't go over them in too much detail because of time restrictions, but they are restrictions on type variables. So if you have type variable t, and then with a trait constraint into iter, t will match bitvec, but not I32. That's because bitvec turns into an iterator, and I32 does not. Furthermore, traits and higher order functions are closely related in Rust, as function closures implement traits. So suppose you replace line 4 in the program with this this map. So here we take the bit vector, chop off the lower 8 bits of every bit, and then collect that into a hash set, making a unique hash set of all the lower 8 bits in the bit vector. Now, here, there's actually a lot of traits that are triggered. So in the beginning, we triggered an into iter trait, which creates an iterator of u size. This determines the function's input type. And then the body, the closure is also treated as a first-class object with a trait, and that's the fn u size to u8 trait. Last but not least, we can make a hash set because this hash set of u8 implements the trait into iter from iter u8. So as you can see, higher order functions are necessary to trigger a lot of these trait functions. Now, for this talk, I'll be focusing on how to synthesize the body. All right, so the insight in our tool is to flatten the closure bodies into the tree search. And here's how it goes. So we continue normally until we hit this into iter API, at which point we let the synthesizer choose the map. And inside the map, we actually see that we can recursively call CrabTree with a slightly different type context, adding the x because the x is newly available. And then we run CrabTree to synthesize the body. And upon the return, we recompute the U8 based off of the return type. And then we keep going as almost a subtree. And so by doing this, we can fold the synthesis into the synthesis of the program. Now, for the evaluation, we ran CrabTree with a set of 30 libraries. 10 each were taken from the Cyrus benchmark, the Rolf benchmark, and 10 new from Crates.io. We ran a bug finding comparison as well as a comparison on 3 metrics, line coverage, branch coverage, and mutation coverage. For this talk, I'll be talking about the line coverage only and for Cyrus and CrabTree. So the gist here is that CrabTree achieves more coverage with fewer tests. Here the graph is coverage over the number of tests. X-axis the number of tests, the Y is the line coverage. Because of this setup, above and to the left is better. That means you're achieving coverage faster and higher. In bitvec, we see that the CrabTree beats Cyrus very quickly and then retains the advantage. In crossbeam, we see that Cyrus is a little faster, but eventually CrabTree beats it. And that's because Cyrus was running with 15 offer selected APIs. These APIs transitively call other APIs, and so this was a fairly advantageous setup. With that said, if we run with the full set of 200 APIs or so, the line would be at 0. So this selection is the source of the strength. However, CrabTree is able to identify the same set and overcome the advantage automatically without any help. We just give it the full set of APIs. Oh. All right, so in terms of what accounts for this gap, we did an analysis of this gap. A few of these are essentially APIs that the previous tool did not support. So for example, iterator APIs just went from 0 to 40 because we're not able to trigger them. Furthermore, all 4 bugs found by CyRust were also caught by CrabTree. Now, for limitations in future work, each of the limitations of CyRust correspond to an area of future work. So we don't support delayed closure evaluation. This is because our approach requires the closure to end at that line, and because of that, things like async are not supported. Supporting those would be a line of future work. We still have manually written templates, which there are existing works to mine templates out of existing code, so maybe tests or use LLMs, those are active areas of research. Last but not least, test execution is still compiling every test, so that's not scalable. To address this, another approach might be to encode the API synthesis in the fuzz driver. This is most recent work is graph fuzz by Green and Vgarnos, which did this. So this is an old line of work, but it's something that's still worth doing because of the scalability limitation. All right, so let's close it out. We propose CrabTree, which is a heuristic-guided DFS algorithm for doing test synthesis, and we propose a flattening of a higher-order function calls into straight-line code synthesis, which allows us to handle traits and higher-order functions. So with that, thank you very much, and I'll take questions.
Thank you.
Yep.
Anyone has any questions?
So that first, right? Very good talk, by the way.
Thank you.
So how deep do you get for some of the bigger cases?
So the deepest we've gone during the run was about 50 API calls. Now 50, yes, but that doesn't mean we hit bugs at 50, right? The bugs tend to be around maybe 10 or so.
I see. So that was my next question. So it seems like in many times there's some kind of small model hypothesis that says that if there's a bug, you will find it before too long. And you're saying that like 10 is like, if you could cut somewhere, cut at 11 or something, and then just focus on. So a very powerful breadth first up to 11 would do well, except that would not be scalable.
Right. So in CyRust, the approach was that they're going to enumerate up to 10. That was their hard cutoff. And so that is the case, but they also were relying on these 15 selected APIs, right? So that's something that I think we will overcome.
Very good. Don't you think that there's a way to combine this?
Yeah, I think that this is an interesting approach. So determining where to cut off is kind of difficult, but I think that's one area that I suppose is line of future work. Come on up.
One question just about your initial comparison between different test generation approaches.
Sure.
So obviously you showed the advantages for like CrabTree supports traits and higher order functions and handles fuzzing inputs. The one question I have is you showed also the size of libraries with number of APIs. Obviously CrabTree performs better than CyRust with significantly more. You also showed Rolf, which from what I saw looked like it had about the same number. Is that accurate, or is the about 100, like is CrabTree a little higher or lower, or is it actually about the same number of APIs as Rolf handles?
Both of those tools, in terms of that axis, right, of the number of API axis, both of those tools are around similar.
Okay.
Yeah, so we're just, if we're winning because of the features.
Sure.
Right, thank you. Anything, I mean, we do have 2 minutes, so if one more question, otherwise fine. Is coverage a good way to assess the quality of the test suite?
That's a very good question. I guess Rohan's not here, so we can't talk about mutation testing, but this was actually brought up by the reviewers, which requested a mutation. We are also winning on the mutation, although mutation has this issue of where the mutants occur, right? Mutant distribution. And sometimes the results flipped because the mutant distribution was skewed. And so some areas that we covered that got a lot of mutants, some areas that Ralph covered or Cyrus covered did not get mutants. So there's, each of these have their own trade-offs. We have all 3 in the paper.
Okay, thank you. And I didn't look at the reviews, I just. Okay, thank you.
No worries,
Thank you very much. Let's thank the author.
Yeah, thank you so much.
Okay, now that we've done Rust, we'll get back to it soon. Now we're going to be testing LLMs, I think. Oh. You are from, which one are you from? From Nanya? Huh? From Hong, okay. I see. Who is from the Linus W? Huh? Oh, okay, okay. All right, well, it's 20 past. Welcome. And now we're going to talk about LLMs for the next talk and still testing. So please, go ahead.
Okay, thank you. Hi, everyone. I'm Ningke Li from Huazhong University of Science and Technology. It's a great honor to present our work here. And I'm going to share with you about our framework that uses logical programming and metamorphic testing to detect factual conflicting hallucinations in large language models. So first, I will give some background on large language models, also known as LLMs and their hallucinations. LLMs have changed our world with their amazing ability to generate text, especially in language processing. But with their great ability, there are also big challenges in the security and privacy. So one serious issue is hallucination, where large language models give some wrong or irrelevant answers during tasks like problem solving. So researchers have found 3 types of hallucinations, including inputting conflicting hallucination, context conflicting hallucination, and fact conflicting hallucination. And the figure here shows what these 3 types are. And the input conflicting happens when the output contradicts what the user asks. And context conflicting includes unrelated information from earlier parts of the conversation. And for the last kind, the fact conflicting hallucination, large language models could give answers that are just not true and which really hurt user trust and model reliability. So here we provide a motivating example. And for current large language model hallucination testing works, they suffer from several shortcomings. So first, they lack benchmarks that contain more complex questions and rely heavily on human efforts. And also, verifying the accuracy of large language model responses is another big challenge. So here, I provide a small example. So take Haruki Murakami as an example, a famous Japanese writer who has always been nominated for but never received a real Nobel Prize for literature. So if we focus on one entity and ask ChatGPT the question, did Haruki Murakami ever win the Nobel Prize for literature? The ChatGPT could answer correctly and answer with, no, he never won the Nobel Prize for literature. However, if we combine 2 entities, things changed when large language models need to do more than one step of inference. So for example, if we ask, did Haruki Murakami and Bob Dylan ever win the same award? And ChatGPT might wrongly say that Haruki also wins the Nobel Prize for literature like Bob Dylan. So these small experiments inspires us that there are 2 challenges. So first, how to automatically create more complex questions that expose more large language model limitations. We get our idea from logical programming. We use logical programming to generate logically sound new facts based on the existing ones, and then generate some new questions. And the second challenge is how to automatically validate answers from large language model outputs. In our testing framework, we use metamorphic relations between the ground truth and the large language model responses to create some task oracles. So the overall workflow of our framework is shown in this figure. So first, we create ground truth facts and triples from reliable knowledge databases. And then we use Prolog and design logical reasoning rules to derive more complex facts. And next, we create Q&A pairs and prompts to interact with large language models. And after inputting the prompt and getting the response, we use semantic structure to check if the response is normal or a factual conflicting hallucination. So let's take a closer look at the details of each module in ROSI. And the first module extracts fundamental facts from the input knowledge data and turns them into fact triples for the further logical reasoning. And we focus on 9 popular knowledge domains and 3 relation patterns from the Wikidata knowledge base. And the algorithm for fact extraction is shown in the figure on the right. We mainly focus to query the database and to get the ground truth facts, like the triples, the subject, predicate, and the object. And the second module derives additional enriched information from the previously extracted factual knowledge using a logical programming-based processor. So we use prolog program, which has 2 main parts, facts R and rules Q. A fact is a relational predicate with a name and entity arguments. And a prolog rule is a horn clause with a head predicate and body predicates. And prolog queries are run against a database of facts. And here we provide 5 reasoning rules: negation, symmetric, inverse, transitive, and composite ones, as listed in the table. So here we provide some simple examples, like the negation ones and the transitive ones as examples. And for negation rules, given a factual knowledge triple, then we can infer the derived knowledge is not valid. And for transitive rules, if object 1 is semantically equivalent to subject 2, and here refers to Kyoto, we can derive a new triple that Haruki is located in Japan. And here we explain the process for applying these rules to the ground truth triples, and it's shown in the algorithm. So first, we design an automatic rule generator to create derivation rules based on the relation categories. And we also generate query problems and match them to these rules for later prolog queries. And then with the rule set, the prolog engine helps us assert all related triples and apply the reasoning rules. And next, we use prolog to find solutions and generate new knowledge triples based on the entities and their relations. For each combination of a subject S and an object O, we create a derived fact with a new predicate. And these derived facts are then used to create some new test cases. And from the derived triples, our benchmark construction module shows how we create question and answer pairs and prompts for automatic factual conflicting hallucination testing. So first, we generate the question and answer pairs. Different relation types have unique features and needs, so we use various predefined templates, as you can see the table above. And next, we prompt large language models to respond by asking them to use their knowledge and inference skills to give clear answers, like yes, no, I don't know, and to our questions. And we also provide a specific example to ensure the responses are generated in the expected formats. And finally, the last module focuses on improving detection of factual conflicting hallucination in large language model outputs by comparing the responses with the verified ground truth in Q&A pairs. So we apply metamorphic relations to spot and evaluate the potential errors in large language model responses. And in our case, metamorphic relation refers to comparing the similarity between the semantic structures generated by large language models and the ground truth counterparts. So we use edge vector oracle and node vector oracles to check similarity. If the similarity is below a satis threshold, it means the large language model's answer is significantly different from the ground truth, indicating a possible factual conflicting hallucination. And conversely, if the similarity meets or exceeds the threshold, the large language model's answer is considered to be in line with the ground truth. And here is our algorithm. So we first we first to check if the answer is start with I don't know, and we consider this is a normal response. And then we construct the semantic structure and calculate the similarity, and then we check the similarity to see if this is a normal response or hallucination. So our evaluation targets the following research questions. The first is the effectiveness of Josie for triggering large language model hallucination issues. And second is the categorization and case studies of these detected issues. And the third is the comparisons among other factual conflicting hallucination evaluation approaches and natural language inference benchmarks. And the last is an ablation study to explore the independence of the logical reasoning rules. And here we list the settings of our benchmark construction and following experiments, and the detailed information can be found in our paper. And so for the first research question, to review the effectiveness of our framework, we evaluate the statistics of test cases generated by our framework, and then evaluate the capabilities of identifying large language model factual conflicting hallucination issues with the generated cases. So we apply Josie to generate a Q&A test benchmark amounting to a comprehensive total of 7,200 test cases. And from the left figure, we can find that among all models, GPT-4 performs the best, showing the lowest rate of hallucinations in Josie's test cases at about 25%. And ChatGPT is slightly worse at 42%. And for smaller open source large language models like Llama 2 7B and Mistral 7B, they perform worse, but their larger versions with 70 billion parameters have higher normal responses rates, even surpassing ChatGPT. And this shows that test cases generated by Josie effectively trigger hallucination issues in various large language models, especially when logical reasoning is required. And we then compare hallucination response across 9 specific domain knowledge, and the right figure shows heat maps of confusion matrices for hallucination rates in these domains based on our tests. So different models have varying strengths and weaknesses across these knowledge fields. One thing interesting is that large language models generally perform worse in natural sciences and mathematics. This might be because Josie's test cases include many astrophysical or mathematical entities, and answering these questions require a deep understanding of astrophysical knowledge and mathematical theory. So we think these areas aren't well covered in the training datasets of the large language models we test, and leading to higher hallucination rates. And this gap in knowledge likely contributes to the model's weaker performance in these domains. And for the second research question, we categorize the hallucination responses in more detail and focus primarily on 2 types of hallucination, error knowledge responses and error inference responses. So we found several contradictory answers due to inconsistencies between incorrect reasoning and correct answers, making them part of both error types. So error inference hallucinations are the most common, making up about half of the results on average. And this shows that the lack of reasoning capabilities poses a broader threat than the use of incorrect knowledge. And so here we provide some of the case studies in our paper. And this is a case study of the error inference hallucination. So a common cause of error inference hallucinations is temporal attribute reasoning. In this example, Mistral 7B incorrectly relies on intuition rather than reasoning, leading to a hallucination response despite, although it has the correct knowledge, it still produced a hallucination response. And for the second case study, this figure illustrates an example of large language model hallucination due to the incorrect knowledge. So when tested with Llama 2 7B, the model fabricated information instead of adhering to honesty principle when faced with unfamiliar knowledge. And then to investigate whether Josie outperforms existing testing benchmarks and methods, we conduct a qualitative analysis as well as a small scale of quantitative analysis of the accuracy of current hallucination detection methods compared with Josie. So Josie automates task construction through prologue-assisted inference, reducing human resource efforts compared to methods like truthful QA and hallueval. which rely on human annotations. And in response evaluation, Josie surpassed simple accuracy-based metrics by considering the structural similarity of large language model responses with knowledge triples and reasoning processes. And for small-scale qualitative analysis, Josie and FactScore achieve higher accuracy in detecting hallucinations due to their decomposed fact and reasoning-based approaches, outperforming similar stream matching methods like COLA and HalluEval. And this qualitative analysis highlights the scalability and accuracy, and as well as the higher automation of our framework. And so for the last research question, we conduct an ablation study to investigate the capacity of each inference rules so that they can be distinctly used to uncover anomalies. And the 4 types of rules are separately applied to generate Q&A pairs. From comparing the 4 inference rules, we can conclude that all of them are effective in generating factual conflicting hallucination test cases and triggering hallucinations in large language model interactions. So to sum up, in this work, we develop a novel factual conflicting hallucination framework. And in this framework, we design and implement logical reasoning-based method for automatic data mutation and benchmark construction. Our framework can automatically and effectively trigger and validate the identified factual conflicting hallucinations in large language models. And for the discussion, we find it challenging to obtain an effective and explainable way to mitigate these hallucinations, because we tried model editing to integrate new knowledge derived from reasoning into open source large language models, but found that the large language models tend to generate a large number of meaningless responses when the editing number exceeds a certain threshold. So we need to explore more efficient mitigation methods. And besides, during the training of large language models, it is important to focus on model honesty, such as how to enable large language models to possess stronger critical thinking and logical reasoning ability. And it's glad to see that the OpenAI's O1 model have already made a big progress in these parts. Also, we think it's promising to looking into more in-depth understanding for large language model hallucination detection and mitigation. So here are some takeaway messages, and we are expanding to an extension version, including metric temporological Q&A verification for deeper analysis. And the white box mitigation techniques have been working in progress. So here we also provide our benchmark and artifact used in our work, and we appreciate it if anyone uses our benchmark for future work. So if there are any questions, please do not hesitate to contact me. And that's all about my presentation today, and thank you all very much.
All right. Anyone has any questions? Oh, thank you, Jens.
You showed a lot of computation. How much time does it take to, how many days or weeks of computation time did it take to compute all the stuff you showed us?
You mean the experiments we worked
your
on the
experiments.
large language models?
Exactly.
Yeah, I think it may take about 3 or more weeks for us to complete all the experiments.
Do you have any ideas for optimizing this in the future? When the next LLM comes around, if people want to repeat what you did, that's a lot of computation time. Do you have ideas for somehow optimizing the process?
You mean testing some new large language models using our benchmark?
No. Testing a new LLM. And trying to draw conclusions of the same kind that you have.
Actually, we're already been working on testing some of the newly emerging large language models, and we think if you don't want to reconstruct this benchmark, and you can just straightforwardly apply the new large language models.
I see. Okay, so it's the construction of the benchmarks that took 3 weeks. But then after you have them, now it's quick to use them again.
Yeah.
Okay, good.
Yeah, thank you very much.
Okay, we better switch over to the next speaker. Thank you very much.
Okay, thank you very much.
And now we have Andrea talking about testing, let's see, distributed systems. I believe. Is all good? Yeah, we are getting to it with a quantum talk that's been happening all of this time. It's just scheduled for the 5th one, didn't you? Okay, let's go ahead.
Hi, everyone. This talk is about leveraging reinforcement learning for testing distributed systems, and it's joint work with Konstantin Rupak and Srinidhi. So distributed systems are widely used for deploying large-scale services and applications, and they usually rely on consensus protocols to work. The way these systems work is by exchanging messages with each other, and because the underlying network can fail and delay these messages, the result is a combinatorial explosion of possible reorderings and possible executions of the system. So because of this reason, even if they're widely used, their verification and testing remains very challenging. So a popular practical approach to test such system is randomized testing. What you actually do is you iteratively run the application and you explicitly simulate the network by randomly choosing the next action, for example, the next message to deliver. And you keep doing this, trying to maximize the coverage of your system states. However, since the execution space is so large, even if you run this for very long, you might still not, you might still miss many possible states of the system. So our approach leverages reinforcement learning to improve randomized testing. So reinforcement learning is a machine learning paradigm where an agent iteratively interacts with an environment by observing its state and taking actions with the goal of optimizing its policy given a reward function. So in 2020, Mukherjee et al. Designed a way to map testing into an RL problem. So the execution of the system becomes the environment, and the state observed by the agent is the actual state of the system, including the state of the nodes plus the state of the network. And now the agent is the testing algorithm which will take actions to the network actions. Now to apply these, there are a few challenges, namely the choice of a reward function for such setting and the choice of state and actions abstractions which determine the resulting space size. So the main contributions of our work are the following. We designed a novel reward scheme for RL-based randomized testing. We discussed the role of abstractions. Then we design an RL-based algorithm to bias testing towards interesting scenarios. And finally, we evaluate our approach, testing real-world consensus protocols implementations. So how do you choose a reward function for testing? I mean, the goal is finding bugs, but you cannot just reward when you find a bug because this is too sparse, and actually, I mean, it happens after you reached your goal. So a good proxy is to incentivize the exploration of new states. And in 2020, Mukherjee et al. Came up with a Q-learning-based algorithm where the reward was given by the negative number of visits for each state. So basically, the more one state was visited by the algorithm, the more negative its value became, incentivizing the algorithm to explore new states. So our approach is conceptually similar. We still have a bonus based on the exploration bonus based on the number of visits, which decays from 1 to 0. And we take the maximum between the immediate reward and the future discounted reward. So intuitively, what this does is to prioritize the maximum novelty along a state sequence. So in the standard Q-learning update rule, you sum them. This means that the algorithm will consider how many times each state has been visited along the path. But with our rule, it ignores how many visits you have along the path as long as it gets to new states, which is the goal in testing. Additionally, it constrains the exploration bonus within 1 and 0, which is important for our bias testing algorithm to ensure exploration there. So let me quickly introduce Raft to use as an example for the rest of the talk. So Raft is a consensus protocol where each node keeps a replica of the log. There is a leader which manages incoming requests, and these requests are appended and committed to the logs of the nodes whenever there is a quorum of nodes accepting them. Then there is a system of term numbers that the nodes can increase upon faults to start new elections if a leader fails. So when testing such systems, there is a fundamental trade-off with the choice of states and action abstractions between testing granularity and the size of the state space. So if we consider network actions, on one hand, one can choose to work with single messages. So each action is delivering specific messages, which will give us a fine-grained interleaving and potentially produce every reordering. But on the other hand, most of these reorderings will not lead to any interesting scenario for the protocol. While if, for example, we just use network partition configurations, we lose the granularity of all the possible reorderings, but in a few steps we can get to interesting scenarios like committing requests or new leader elections. Similarly, for the system states abstraction. So what kind of information do we include in the system state that we expose to the RL agent? So the information we include there will make the algorithm to explicitly explore the different values for such states of the system. But on the other hand, you definitely want to remove redundant information because this will lead to an even larger state space, and you don't want your algorithm to explore, for example, reorderings of the IDs of the node, which are not meaningful. So the type of state coverage you get strictly depends on the choice of this abstraction. So if we think about Raft and you exclude the log information, then your algorithm will definitely explore more quickly different terms and leader elected, but you lose the granularity of exploring different configurations for the logs in such states. So to tackle both the general problem of the space size and the choice of the abstraction, we designed a way to bias testing towards interesting scenarios. So the tester can define subsets of states through predicates and can build an increasingly specific sequence of such predicates to guide the algorithm towards interesting parts of the state space. So our algorithm takes this input of predicates, its sequence of predicates as input, with the last one defining the target subspace to explore. And then on top of the standard exploration bonus to increase the coverage, it provides positive rewards whenever the execution gets to these defined subsets of the state space. So in this way, the tester can define, can target specific subsets of the state space where you might have insight about being more critical or where it's more likely to find bugs. And at the same time, this helps to keep the abstraction, more information in the abstraction, because in this way, if we think about the previous example, you can keep the log information, but still you can push the algorithm to explore different leader elections, and then within that subspace, the algorithm will explicitly explore different logs configurations, so you have better granularity of your, in the exploration of your target subspace. So these predicates have to be manually designed by the tester. So what we did in our evaluation, we just took generic predicates for Raft. So for example, entries added to the logs, or nodes reaching higher terms, or leader elected in higher terms, or more specific ones. For example, having 2 logs with a difference in their lengths, meaning that the protocol should handle the synchronization of this outdated log, which might, for example, be more likely to lead to bugs. So just to give an example, one predicate might be having an entry committed in term 2, at least one entry committed in term 2, and one possible waypoint to help the algorithm to reach there is having one leader elected in term 2, because this is mandatory to commit a request in that term. So in terms of additional required instrumentation, on top of what you need for randomized testing, which is capturing the messages and controlling the network, you just need to expose the required state information during the execution such that you can provide it to the agent. And then you need to write the code to map the system execution into an RL environment, meaning that the state information from the system should be wrapped into an environment state. And then you need to ensure that whenever the agent takes an action, this should be applied in the system execution. So to evaluate our approach, we tested 3 real-world protocol implementations, 2 based on Raft and 1 on Paxos. And in our experiments, the actions are partitions configurations for the network, plus external requests to be committed, plus crashing single nodes. And the state abstraction is given by the state of the nodes plus the current partition configuration of the network. And for the node states, we consider the protocol relevant information like term numbers, the role of the node, the log information, and so on. And for the result, we ran different testing iterations, and we average the results. So the first question is, do we get better coverage with our unbiased RL-based exploration algorithm? And the answer, so these plots show the state coverage over testing time. And we compare with the previous approach from 2020 and with the random baseline. So in the benchmarks, we outperform random. So our approach is the red one. In the benchmarks, we outperform random, and we are comparable with the previous approach. In some benchmarks, we are better, but this is kind of benchmark dependent. So the second question is, can we actually bias testing towards specific states and subspaces of executions? So for doing this, we provide waypoint RL with the corresponding predicate sequence, and we measure the coverage of states of that target subspace. And here we compare with the 3 unbiased baselines that I showed before. And for this, we get significantly better coverage for most of the predicates, actually 20 out of 26 across all 3 benchmarks, meaning that we can actually bias the testing executions toward specific subspaces. And the third question is, does biasing lead to better bug finding? So during our experiments, we measured the average frequency of bugs occurrences. And this table shows it for one of the benchmarks. And as you can see, so each row is a different bug or crash. And for most of them, there is at least one bias testing scenario that achieves higher frequency, meaning that it would be easier to discover them and reproduce them by biasing testing toward those scenarios. Thank you.
So you had this thing in the beginning that the previous work had in the reward function minus something, and you change it to 1 divided by something, blah blah blah. Do you but then you have a whole bunch of other things you talk about. Do you have a way of dividing up the success into what success came from changing the reward function and what part of the success came from all the other stuff you did?
So the success of changing the reward function in the unbiased setting, so just for increasing coverage, is partial in the sense that we don't have a significantly better coverage for the unbiased setting. But so one thing is we still believe this max operator is conceptually good for testing in the sense that you really want to get to the new states. You don't want to balance the exploration of the states you know. Another point is that our approach, we need our approach to build the bias testing on top of it, because when you have a negative value, you cannot balance at all between the exploration and the exploitation of these waypoints. But by providing a positive value, you can choose the reward you give in the bias testing as a hyperparameter, and you can somehow balance between how quickly the algorithm will converge to one of these executions whenever it finds a waypoint. So this is also required for the second part of the approach.
You had these very large error bars, so like in this graph you show at the end, the yellow part there is like really wide. Why is it so wide compared to the other ones?
Because I think out of at least 10 different iterations, I think for a few of them, probably the algorithm completely failed to get there, so the coverage. So when you compute the standard deviations, I mean, there's a chance that it fails to actually converge to that type of subspace. So yeah, you can have a high variety of the results. But, yeah.
Are you coming from the distributed systems applying this? This project, how did you basically end up doing this? Were you coming from distributed systems?
I think more from reinforcement learning.
So yes, you just didn't apply it. Is there then other places where you think? Oh, you came from reinforcement learning and applied it to this distributed systems problem. Mm-hmm. Is there a similar thing you think that you can see in PL or otherwise?
Or is it just not sure.
People do consensus and other stuff. Oh, it's okay. I was just asking if you have other areas where you think it may apply, but it's okay.
I mean, it depends. You mean leveraging reinforcement learning to guide the search?
Publishing the reward to actually guide your search for the distributed system. I mean, is it a generic thing you can keep applying to other things, or was there something special about distributed systems?
No, I mean, I think the distributed system setting is because you really have this very large space, and you can really use this idea of providing insight on where you want to explore, right? So, but yeah, the approach is somehow generalizable, but somehow you need you need a place where you can actually use it, right? So I think distributed systems are a good candidate because you really have this problem that state space is too large, so you might need to do something like this.
Okay, well, thank you. So we have another Rust talk again. And then at 5:20, we will have a talk on quantum that may or may not happen. We'll measure and find out at 5:20. Okay, no, it's something is, so play again. So that's another window, that's another desktop, don't worry, everything is fine. Yeah, there we go. All right, so now we have the second to last talk on Rust again. Still staying on the testing theme, so please.
Yeah, so good afternoon, everyone. It's 5 p.m. on a Friday, so thank you very much for sticking with me instead of going off to the pub. I'm Andy. I'm going to talk about how we found bugs in the Rust compiler. When you compile code, you would have faith in the compiler that it's going to... Yes, you have faith in the compiler that's going to correctly translate your code into equivalent machine code. Unfortunately, compiler authors are also human, and compilers can have bugs like our other software do. Now, ideally, we'd like a piece of software as fundamental as compilers to be fully verified. And there are indeed fully verified compilers for languages like C and ML. But these compilers were purpose-written for static verification. They often sacrifice generated code performance in favor of the ease of verification and are nowhere near as complex as the more industry-adapted compilers. We are still quite far away from being able to fully verify a compiler that wasn't purpose-written. Another approach, which I'm sure you have seen many times today, is fuzzing, as known as randomized testing. Here, we generate a random program, compile it, and see if it runs correctly. And of course, for a complete random program, we don't know what's the right behavior and what's the wrong behavior. So we augment this idea with differential testing, where we compile the same random program using different compilers or different compiler settings and compare the results. We expect them to be the same, but if they're different, then at least one of these compilers have a bug. Using this approach, we developed the first random program generator for the Rust language. We call the generator RustLantis, that is able to find new miscompilation bugs in the official Rust compiler. And I'll talk about how we did it. So when making a random program generator, the first thing to think about is what to generate. The Rust compiler compiles your source code in stages, broadly divided into the front end and the back end. The front end is responsible for things like parsing, type checking, ownership, and borrow checking, and then eventually lowers your code into an intermediate representation called the mid-level IR, or MER for short. Some optimizations are performed on MER to reduce code size and improve performance. This is then lowered into LLVM IR, more optimizations are performed, and machine code gets generated. We are the most interested in these optimization stages because they are the most likely places for correctness bugs to hide. However, if we were to generate just normal Rust code, we call it surface Rust, then we have to confront all these checks in the front end. They are very important, and they are there to uphold all the guarantees, safety guarantees that Rust compiler has, but they have been extensively tested by others, and they do not meaningfully affect these optimizations if we can independently guarantee that the code we pass to the optimizations are valid. Additionally, the Rust compiler, especially at the MER stage, is allowed to transform code in a way that is correct, but would otherwise break the borrow checking rules. So generating surface Rust would actually restrict the diversity of our programs. For these reasons, RustLantis will not generate surface Rust and will instead produce the mid-level IR directly. Here is a very simple Rust function. It assigns a value to x, increments it in a loop, terminates the loop once x is 10, and returns a number. This is how this function looks like in MER. It is a control flow graph made up of basic blocks. Each basic block can contain 0 or more statements and exactly one terminator, which transfers the control flow from one basic block to another. A terminator can have mutable targets conditioned on the value of a variable, like we see in the match terminator in BB1. This is equivalent to the switch statement in C. One characteristic of MER is that because this is a stage after all the checks in the compiler, all code is unsafe. That means none of Rust's normal safeguards apply. There are no borrow checks, no bounds check, no lifetimes. This is good because it allows us to generate the full range of possible programs, but it also means that our generated code can contain undefined behavior, UB. This function triggers UB by casting a byte that is not valued 0 or 1 to a Boolean typed variable, breaking the value constraint on the Boolean type. When UB is present, there is no write behavior. The compiler is allowed to do anything. And since we are comparing the result of different compiler settings or different compilers, if our generated code contains UB, we cannot be certain that it represents a miscompilation. For this reason, RustLantis must prevent UB while maintaining the diversity of the programs that we generate. With that in mind, let's have a look at how RustLantis is implemented. We generate programs in a top-down fashion. We start with an empty function, declare some local variables, and generate statements to a basic block one at a time. The cursor represents the location of the next statement to be generated. And after a random number of statements are generated, we produce a terminator and then move our cursor into the basic block it targets and continue there. We create a new function whenever we generate a call terminator, move our cursor into there, and start generating basic blocks and statements. We return to the previous function when we produce a return terminator, and the whole program finishes generation when a return terminator is produced in the first function. Note here that RustLantis' generation flow is in lockstep with the runtime control flow. This allows us to keep track of the runtime state of the program for the purpose of avoiding UB, which may sound restricting, but I'll talk about the solution later on. In this example, you can see that there are variables or fields of variables on both the left and right-hand sides of the program, highlighted in bronze. These expressions are called place expressions. They represent memory locations. Place expressions always start with a local variable and is followed by any number of projections, which can be a tuple or a struct field, an array indexing, or a dereference. We cannot generate place expressions completely randomly. A Boolean variable cannot be indexed, that wouldn't compile. An uninitialized variable cannot be read, that would be UB. A pointer pointing to a deallocated stack cannot be dereferenced, that will be also UB. To keep track of what places we can or cannot generate, we make use of a data structure called the place graph. It records all the reachable places at the current point in the program. Whenever we declare local variables, we add the local variable and all of these fields as nodes to the place graph, with edges in between them representing possible projections. We also keep track of point-to relationships by adding edges whenever a reference or a raw pointer is created, which allows us to know where a reference or a pointer is pointing to at all times. The place graph additionally records the value when a place has been assigned with a literal, and it is interprocedural, allowing pointer-typed parameters to be dereferenced in other functions. When we need to generate a statement, we query the place graph to obtain all possible candidates for the current context and pick one at random. When we are in a context where UB is possible, such as division by 0 here, the information in the place graph allows us to generate statements that we know for sure will not cause UB. Besides values, the place graph also helps us in generating programs containing complex control flows. This is desirable because a lot of optimizations are based around loops and branches, which is introduced by the MASH terminator. And in this example, let's say that RustLantis in the place graph knows the value of x would be 4. So the arm with 4 will be the next basic block to generate. But this also means that arms with other values will never be taken. This allows us to add additional branches to a previous basic block, creating a loop structure, knowing that you will not be taken at runtime and thereby having no chance of introducing UB. We can also create what's called decoy blocks, which are populated with the content of a random existing basic block, including the terminator, which could call functions we have already called or visit basic blocks we have already visited. Since the value of x depends on a parameter, the compiler cannot tell, at least not through intra-procedural analysis, that only one branch will ever be taken. Therefore, it is forced to analyze and optimize this complex control flow, which exposes bugs in the relevant optimization passes. In all of the examples I've shown you so far, there have been references and pointers. And some of you may know that Rust have an extensive set of aliasing rules governing these. Violating any of them would be UB. For example, one of the rules says that if a place has been referenced by a shared reference, and you've written to it by whatever mean, then the lifetime of that reference has to end. If you use it again, that is UB. In this code, B is a shared reference to A, and B is invalidated after A has been written with the literal 42. The line in red reading through B causes undefined behavior. To prevent generating code like this, we maintain a borrow stack similar to the one introduced in the stacked borrows aliasing model. We keep track of references and row pointers in a stack for each place and add an entry onto the stack whenever we create a row pointer or a reference. Only references and row pointers with corresponding entries on the stack can be dereferenced. So right now we can generate a statement that dereferences both A or B. But if we were to then generate a write by dereferencing A, then everything above A's entry in the stack is invalidated, preventing B from being used later. For the fuzzing harness to tell whether the program behavior has changed from one compilation to another, we print some of the local variables to the standard output. However, even if the program is completely UB-free using the techniques we've talked about so far, we still have one other issue to contend with, which is non-determinism. Some variables are allowed to have different values on each run, such as pointer addresses. So we just can't print pointer type variables. But that's not enough, because non-determinism can leak into values of other types. An integer could be non-deterministic if it was cast from a pointer. A Boolean could also be non-deterministic if it came from comparing the addresses of two pointers. If these values are used in further expressions, then non-determinism would infect the rest of the program, preventing us from being able to tell a compiler bug from normal behavior arising from non-determinism. Globally, therefore, we must exclude some of the operations from being generated, which are pointer to integer casts, pointer comparisons, and floating point to integer transmutations, also known as bit casting in some other languages. This is due to the NaN value being allowed to have non-deterministic bits. Utilizing all of these techniques I've shown you, we've generated a whole bunch of programs and targeted 4 testing backends. Rust with LLVM, which is the default code generation backend, but at different optimization levels. CraneLift, which is an alternative code generation backend to LLVM, and Miri, which is an interpreter that can detect UB at runtime, confirming that our generated code is indeed UB-free. In total, we've discovered 22 unique bugs that were previously unknown. All of them have been reported, and all but one have been fixed. 16 of these are miscompilations, where the user would have no idea that the compiled code is wrong. I'll give you an example of a bug we found in LLVM. So this function checks if something does not equal to the NaN value of double precision floating points. By the standard, NaN does not equal to anything, so this comparison should always be true. When cast to an integer, it should always be 1. But when compiled to x86, it returns 255, which is not even a valid bit pattern for Booleans in LLVM. There are many other bugs, interesting bugs we found. Some of them have been hidden for years, and some of them were serious enough for the patch to be backported into the latest release. And besides the techniques I've shown you, there are other techniques we've used to generate things like structs and pointer arithmetics. And due to time constraints, unfortunately, I cannot show you all. But I hope you can see how RustLantis is a valuable tool in improving the quality of the Rust compiler, and we are helping Rust to live up to its promise of a safe and performant systems programming language. I strongly encourage you to read the paper, and the source code is available as well. Thank you very much.
Any questions? Can you come up to the microphone so that the video can record it, please? Thank you.
Thank you for the talk. In your the Boolean example, do you know why the assembling code is wrong?
If you dig into the issues, you can probably find out. I can't remember off the top of my head.
Oh, okay.
Yeah. Actually, well, more specifically, there's a parsing LLVM after optimizations called, it converts the IR into a directed acyclic graph and uses that to select instructions on x86. And that, I think that's the part that gets it wrong.
So is it related to the optimization process, or it's just the code generation?
It's the code generation, yeah. This is specific to x86.
I see.
Yeah.
Thanks.
Thank you.
Good talk. You said in the beginning that you got to generate intermediate code directly because you're going after bugs in the optimization phase of the compiler. In retrospect, those programs that you did generate and that gave you this list of bugs, could they have been generated from source, or is that just you can see that those programs just absolutely are not really relating to any Rust source code?
So theoretically, from the control flow perspective, all the MER I generated are reducible, meaning that they could be rewritten into normal Rust with like if and for loops and things like that. But I believe there are extra statements that's always added when lowering from surface Rust to MER that could prevent things from being triggered. I cannot tell for certain. I didn't do that experiment or study that extensively.
So I'm asking because it's if it was possible to get those programs from source, then one could imagine that you could redo your whole research program here and just do Rust source instead, and use the compiler to the level of intermediate and then find bugs there. Maybe?
That would be. I think that would be possible, although I'm not sure about the benefit of doing that, just because we are the most interested in doing the testing the backend stuff, right?
That's fine. Yep.
Anyone else? Okay. Yep. David.
Thank you for the talk. Very good. One question I have is you mentioned that it would be hard to generate Rust code due to all of Rust's type checking and constraints and all of that. But then throughout the rest of the talk, you walked through how you were able to generate in the intermediate code that would pass all those type checks or would maintain the same behavior. Maybe I'm just missing something, but what's the gap there? What's the difficulty that makes it harder to generate raw Rust code but not intermediate code?
So I kind of lied a little bit. The MER is not completely typeless. Like, as I said, you can't index a Boolean variable. In the strictest sense, the Rust type system is a linear type system which has ownerships. So moves would be called by the type checker, whereas that's not something that is called at the MER stage. So there are parts of the full Rust type system that gets checked, but some of them isn't. Yeah.
Cool. All right. Thank you. And just to clarify, all of the borrow checking has been done at the high level by the time it gets to.
That's correct. There is no borrow
checks.
checks there.
Completely, fully free of all of the lifetime and all of that stuff.
Well, okay. Again, technically, borrow checking is done on MER. But MER has different phases. We do it after the phase we inject the code into the phase that's after borrow check. So there are absolutely no borrow checks at the phase that we inject, yeah.
Okay, cool. Thank you very much.
Thank you.
All right. And now for the final talk of the conference. We already measured, it is happening. It's now testing quantum. Has Hakju left already? Has Hakju already left?
So,
Hakju already left?
yeah, my device is.
Run away. It's okay. For the final talk, so Jung-Ho is going to talk about quantum testing, so please go ahead. Okay.
Hi, I'm Jung-Hoon. Thanks for coming to my talk. Today, I'm going to present our work on statistical quantum program testing. This is a joint work with Chang-Gu Kang and advisor Hak-Ju Oh at Korea University. First, let me introduce some key concepts in quantum programming. A quantum circuit is the fundamental building block of any quantum program. This diagram shows the implementation of a quantum operator, which performs addition on quantum states. In quantum circuit, each wire represents a qubit, and each symbol on the wire represents a quantum gate. And each program state is expressed by a state vector. To run the circuit, we need an input state vector. And after we run this circuit with given input state vector, then we also get the output as a state vector. Especially in quantum mechanics, each quantum state is represented as a ket vector. For example, this ket vector expresses the vector in 4-dimensional complex space. And bugs can also occur in quantum programming. Even a single misplacement of a quantum gate can induce unintended terms in the output state vector. For example, if we add unintended Z to 0.02 gate into the 4-qubit operator circuit, then it introduces these two unintended terms in the output state vector. So we refer these as bugs, and they violate the intended specification, and in this case, they're the correct addition. So we say that the program state pcat is correct if pcat is the same as the given expected output state ecat. On the other hand, it has a bug if they are not the same. And we can express such incorrect state as a linear combination of expected ecat and unexpected ebotcat with some coefficients as below. So this is the problem definition for our work. The goal is to determine whether the program state matches the expected outcome. First, we need a quantum circuit, the input state, and the expected output state. Then we evaluate the program state pcat, leading to one of two results. In the first case, we detect a bug, which is the unexpected term ebotcat. In another case, we find that the program state is nearly correct with epsilon closeness, with statistical confidence. Well, I will explain the reason why I said statistical assurance in a few slides later. Well, in classical programming, checking the program state is quite straightforward. For example, if we want to assert that a variable x is equal to 1, we can find it out by simply reading the data register. In contrast, in quantum programs, there is a limitation that prevents us from directly comparing the qubit registers in the same way. The reason is called Born rule, which is we lose the quantum state as we measure it. After we read the program qubit registers, which is called measurement, then the quantum state immediately collapses into one of their bases, which is if we read the register, then we get ecat or ebotcat only because they are the components of bases. And this measurement procedure is irreversible, which is we lose the exact value of alpha and beta after the measurement. As a result, we can only consider the statistical assurance after the measurement. To test the quantum program with respect to this issue, there is one straightforward way. We can just sample the measurement data from the program state. The whole process of this method is as follows. First, we prepare the program state by running the quantum circuit, and then we measure the program state. If we measure the unexpected state, ebotcat, then we can conclude that the program has a bug. On the other hand, if we measure the expected state ecat, then we should go back to the first step and repeat it until we get the sufficient assurance. Therefore, this naive sampling method requires an excessive number of measurements. To detect a bug, we need even more measurements as the value of B decreases. For instance, in this quantum program, where we introduced a buggy gate to detect the ECAT state, we need an average of 1,000 measurements. Here, measurements refer to the number of times the quantum programs must be executed, which means the circuit must be run for 1,000 times again. In another case, to verify the correctness, we also need a large number of measurements for assurance. For example, to ensure the probability of the unexpected term is smaller than 0.001 in this example, we need about 9,000 measurements, which necessitates running the circuit a substantial number of times. In this work, we addressed this issue by utilizing the amplitude amplification method. Given program state PCAT, we apply the amplitude amplification before the measurement. Then we can increase the probability of measuring the unexpected term, and as a result, we can reduce the number of measurements required to detect a bug, which is eBootCat in this example. Here, one issue arises with this approach. While we can use the Grover iteration for amplifier, which is a well-known amplification operator in quantum computing, to amplify the ECAT state by applying the Grover operator G multiple times, then it doesn't guarantee the amplification without any prior knowledge of the source state. And this is called souffle problem. Instead, to address with this issue, we opt for the fixed point amplitude amplification, which is called FPAA, in our work. FPAA is very effective amplifier for finding the specific number of iterating Grover operation. It guarantees the existence of L star such that L star times of repeating the Grover operation amplifies the probability of measuring eBootCat, which is the bug, with desired assurance. In the verification process, we only need a few measurements because we amplified the probability of detecting the error state, eBootCat, if it exists. Additionally, the program state is also preserved if no bug is present. Therefore, by utilizing FPAA, it requires fewer measurements compared to the naive sampling method, making it more efficient in terms of measurement requirements. In addition, for bug detection, since we amplified the probability of detecting unintended terms, eBootCat, the unexpected state eBootCat can be detected with just a few measurements. For example, if you amplify the probability of measuring eBootCat as 0.95, then we only need 2 measurements are expected to be sufficient. Now we know that the FPAA-based quantum testing is effective in terms of the measurement requirements. For example, in our working example from previous slides, we can reduce the required number of measurements from 1,000 to 2 for bug detection and about 9,000 to 5 for verification. Well, it seems very powerful, but there's one question still remains. Isn't it too expensive? Which is, how about the overhead for utilizing the FPAA? The answer is, in some cases, using the FPAA is more expensive than the naive sampling method. If the probability of detecting eBootCat is high enough, fewer measurements are needed. For example, in this case, where B is 0.05, we could consider simply using naive sampling with 20 measurements, which is quite worthy of consideration. So we need more efficient strategy, which we propose by running multiple FPAAs with a smaller number of Grover operations incrementally. In this study, we refer to this strategy as SFPAA, which sequentially runs LFPAA in increasing order. Here, L refers to the repetition, the number of repetition of Grover operation. For example, if we choose such S1 strategy S1, we first run 0 FPAA with 100 measurements, and then 9 FPAA with 3 measurements, and so on. With this incremental FPAA strategy, it requires significantly fewer Grover operations, which reduces the overall running cost. For example, using the strategy S1 in the slide before, we need an expected 9 Grover operators to detect the first E-boat cat during the repeated measurements. In contrast, directly running the full FPAA requires 34 Grover operators. Now I'm going to talk about how to find such strategies in terms of the number of Grover operations. Our approach is based on random search with heuristics, but there are 2 additional constraints. While randomly generating the strategy S, not all S are valid for testing the quantum program. First, it must guarantee the bug detection, and second, it must provide the sufficient assurance. And there are a few more conditions, so for more detailed formalization and analysis, please refer to our paper. Since we are testing quantum programs, the best way to evaluate our method would be to run it directly on real quantum hardware and compare the execution times. However, as quantum hardware is still under active development and mature systems are not yet available, we instead compared the total count of executed moment in the circuit for each method. Here, a moment refers to a unit time slice used to synchronize operations when executing on actual hardware. We prepared 3 randomly generated strategies, S1, S2, and S3, for our case study, and compared them to the naive sampling method and to S-naive FPAA, which runs FPAA without a search heuristic. The results show an average verification cost reduction of 58% compared to the naive sampling method. Although S-naive FPAA shows the best reduction rate, which is running FPAA without a random search heuristic, but it presents a challenge for bug detection, and I will explain about this in the next slide. Our method is more effective for bug detection when the probability of detecting an unexpected term, denoted as B, is smaller. When B is 0.001, which is quite small, our search strategy achieves a 40% average cost reduction compared to naive sampling method. Furthermore, our approach significantly mitigates the loss in benefits of using FPAA. In the S-naive FPAA approach that I mentioned at the slide just before, the loss can be as severe as minus 120%, but random search strategy reduces this to just minus 29% on average. This demonstrates a compelling trade-off, making our search strategy a better choice for enhancing FPAA performance. So in this work, we utilized FPAA to test quantum programs. I didn't go into the detailed working of FPAA in this talk, but the core principle is that it transforms the amplitude of the unexpected term from B to some function, PLB. And for more details on FPAA, please refer to the paper. In essence, FPAA operates as an engine that transforms the amplitude, but there may be more optimal quantum circuits and functions for this process. One well-known method to construct a quantum circuit for function f is called quantum singular value transformation, which is called QSVT. So combining these methods could be a promising future direction. To sum up, the problem we addressed in this work is quantum circuit testing. To improve this process, we propose a new scheme for design to enhance efficiency. The core idea of our approach is the introduction of FPAA, with a focus on cost effectiveness. by applying a well-defined FPA strategy that we proposed, we show that our method is highly effective for testing quantum programs. So this is the end of my presentation. Thank you.
Jens, please.
I have two questions. It was a good talk. In one of the first evaluation slides, your x-axis was going all the way to 500 qubits.
Yeah.
How did you
50
do?
qubits, I think.
Could you show again? Maybe I need new glasses, and that's my real question.
Sorry.
Let's get this under control.
I think. You mean this slide?
Not this one. One of the other ones.
This
500
one?
qubits.
Yeah, maximum. Okay.
Huh?
Yeah, that's true. 500 qubits.
How did you do experiments with 500 qubits?
Oh, we did not execute it on some real hardware or.
No, but how did you execute it with 500 qubits? What did you do?
Well, the quantum hardware is still in development, and.
No, I understand. What did you do?
Sorry?
How did you get experiments done with 500 qubits? What did you do? There are numbers on the graph. I just want to know.
Okay, I see. Sorry. So we counted the depth of the total executed circuit, such as.
So the y-axis is just the depth of the circuit.
Why? Y-axis is the reduction rate. Okay, so we compare.
Reduction in depth. Okay. So
yeah, reduction in
depth.
Yeah, true.
That leads me to my second question. So am I understanding correctly that you're expecting the output to be one out of two states, either the right one or the wrong one, and that's it?
Yeah, that's true.
So what often happens on noisy hardware is that the state you expect will like be very likely, let's say 90%, and then the remaining 10% is distributed over everything else because there's noise in the system. Then your method would be less effective, I guess, if there are many wrong ones.
Yeah, that's true. That's the one of our limitation. And to model the noisy situation, we need to deal with the mixed state, right? But our method does not. Our method only deals with pure state. So I think the reason is FPA method does not work for mixed state. It is only for pure state. So to deal with some noisy situation with dealing with mixed state, then I think we should consider we should work on the future work for dealing with some mixed state situations.
Okay, very good. I understand. Thank you.
Thank you.
Right. Thank you. I guess if there is last chance to ask OOPSLA 2024 question. So in that case, well, I'm Simon. Thank you very much.
Thank you.
And yeah, thank you.
Thank you.